Ankur sir, very good afternoon. Shall we start, sir?
Yes, please. Yeah, we can start.
Thank you. So, very good afternoon, and once again, welcome for the session of today's second session, but total is fifth session. And the title of this session is Roadmap and Challenges of Battery Storage for EVs, and which will be handled by Dr. Ankur Bhattacharya from BITS Pilani, Hyderabad campus, Hyderabad. So thank you so much, sir, for accepting our request, and warm welcome to this session. Basically, Dr. Ankur Bhattacharya did his BTech in Electrical Engineering from West Bengal University of Technology in 2010 and MTech from Bengal Engineering and Science University, Shivpur, presently known as IIEST Shivpur, in 2012. He has awarded PhD in Renewable Energy from Indian Institute of Engineering, Science and Technology, Shivpur, in 2018. Presently, he is working as an assistant professor in the Department of Electrical and Electronics Engineering at BITS Pilani, Hyderabad campus, India. He has over 8 years of teaching and research experience in the area of electrical engineering. He has published 35 research articles in reputed international journals, conferences, book chapters, and a book in the area of renewable energy and battery storage. He has also filed 3 patents so far in his area of expertise. His present areas of research interests are battery energy storage system, electric vehicles, microgrids, and power electronics converter. So once again, welcome you, sir, for this session. I'm now handling this session to you, sir. Thank you so much, sir, for accepting our request. Yes, Ankur, sir, it is to you, sir.
Hello, am I audible?
Yes, sir. Yes, sir. You're audible.
Okay. So let me switch on the video as well, if possible, if the internet connection permits. Let's see. Okay. Fine. So thank you very much, Dr. Kundan. First of all, I would like to thank Dr. Kundan for inviting me to talk about this emerging topic on electric vehicle and the growth, of course. So let me share the screen, and let me share the screen first before I start. So is it visible, the screen?
Yes, sir. Yes, sir. Your slides are visible.
Let me go to the slide mode, PPT mode. So it's is it visible, right, to all?
Yes, sir.
Okay, fine. Thank you. So so today's I will talk about this under the theme of emerging trends of development of electric vehicles, and my topic will be specifically roadmap and challenges on battery storage for electric vehicles. So with this, let us start today's discussion. It will be of around 1.5 hours, and then we can go for a question and answer sessions if we have. So to talk about this, if I can divide into contexts, having this into motivation, of course, any talk or any topic needs a motivation initially, and then we discuss the growth of EVs for battery storage, then the role of energy storage in EVs, then its challenges we face, possible solutions, and finally we can conclude some solutions, of course, at the end of this talk. So to begin with, this motivation, if you can say, as we know that globally the transportation sector is contributed by the EVs mostly, and electric vehicles, they contribute, and to avoid this greenhouse emission, we need the implementation of EVs in more and more. And the existing transportation system, mostly they run on fossil fuels, and they contribute to 23% of the global greenhouse gas. And out of this, this transportation sectors, we have the roadmaps of the road transports of 75% we're having at present globally. And to be very precise, we can say that in the coming years will increase more and more. And the second point, involves the green transportation, as we can say, that electric vehicles, if we consider about the electric vehicles, then it means the green transportation means less carbon emission. We cannot say zero carbon emission, we can say less carbon emission with the help of the batteries. And they are mostly having these electric bikes, 3 to 4 wheel vehicles, of course EVs, and the green trains. They are presently focusing on focused on the many countries. And the batteries are the key components, as we know, that for the powering these electric vehicles. And of course, I'm naming as a transportation system because in transportation, mostly it includes the vehicles in the transportation mode. And for the EVs we talk about, then batteries are automatically coming in as a heart of the system to power the whole operation. And of course, in addition to the batteries, we also have to keep in mind that to ensure least carbon emission to the atmosphere, we need utilization of more renewable energy sources of solar, wind, etc. These are the available resources in our majorly in our across the globe and as a power supply to ensure eco-friendly transportation. So with these motivations and this present scenario, let's talk about the global growth so far in last decade of vehicles in the world. So left graph shows the region wise and the right graph shows the vehicle pattern wise. So you can see the exponential growth in both the cases in the last 10 years. We are having this, especially in the countries of China and Europe and the United States also. They are developed a lot, and the rest of the countries also they are adopting this green transportation system to prevent those greenhouse gas emissions caused by the vehicles. And the right side graph is the transportation mode, that is the PLDV. It is majorly contributed by PLDV, means passenger light duty vehicles, this blue one, and the LCV means light commercial vehicles. They mostly contribute, and apart from this, electric buses are also being now popular for the mass transportations. And also for the material transportation, trucks are also now being adopted electrically, totally electric or battery fed. So apart from this PHEV or plug-in hybrid electric vehicles, we go for the electric vehicles. Here we talk about, because the batteries are the concern. Now, with these two records, we can say the study says that in the upcoming 10 years, we are having the roadmap or the projection of this as per the stated policy scenario, as per the sustainable development or the world scenario. We are having these two areas where we can say that state policy wise, we are having globally, of course, it is contributed by this battery operated vehicles. BEV is nothing but the battery operated vehicle, and PLDV is, as I just told, passenger light duty vehicles, and this is LCV or the light commercial vehicles. All we are talking about mostly the BEV, battery operated vehicles, and you can see the growth which was there around in millions. It was there in 8 to 10 millions as of now. In 2020, it comes to around 150 million in numbers. So of course, in the sustainable development, we have a much more target high. So to achieve that, we need to implement more and more electric vehicles, and mostly battery operated vehicles are there, because these are the batteries are the concern. Your storage, I can say, power supply, which can ensure or which can enable the zero carbon emission target. So we can have this latest data. And in India, especially if we talk about, because why I am discussing with this, because we need to have a brief background on the electric vehicles and the growth of EVs in our country and the globe. Then we can estimate the need of battery storage, and for that, what are the challenges and how to mitigate those. Let us slowly go to that. So EV stock in India in last decade, we're having around say 15,000, around 10 to 15,000 of approximately EV growth. But these are considered as BEV only, means battery operated vehicles only. There are PHEVs are there, of course, hybrid electric vehicles are also being popular, but we are talking about the mostly that sector where the battery operated vehicles are concerned. So around 15,000 is very less as of now compared to global growth, but of course, slowly the target is being achieved by the different policies on the EVs in upcoming 10 to 20 years. Keeping that growth in mind, we have to now go to the, say, battery as a for the beginners. If you want to see that electric vehicle component, if you can say, the electric components of the vehicle consist of right from the output or outlet or charging station. Charging equipment is there. We have to charge the battery, and to charge the battery through proper controllers and converters. That's why the power electronics circuit board is required, where the converters and inverters are there. And from there, it is a central controller, and from there, battery is getting charged. And the battery also is used to power the motors as a drive system. So it is a definitely a different area of research, that traction drive system of vehicles. But I will not go into that. I will rather focus on the battery storage part. So keeping that major components of electric vehicle in mind, let me share some important study on batteries for electric vehicles in our country and of course the globe, let us say. So starting with the batteries for EVs, as we know, that it enables, see the study says that it enables, as per the Global EV Outlook magazine 2021, we can say that 30% of the required reduction of carbon emission batteries can contribute. And that is required in the transportation sectors, of course, in addition to the power sectors. And battery-powered vehicles promote green transportation. This is the major interest for implementing battery-operated vehicles. And between this 10 to 2018, that demand of battery storage grew up by 30% annually and reached volume of 180 gigawatt hour in 2018. So globally, it can reach up to 2,600 gigawatt hour of battery storage requirement within 2030. You can see the exponential growth globally, the battery storage need for the implementation of vehicles. And these BEVs accounted for 2/3 of the new electric cars registration globally in 2020, despite COVID-19 pandemic. See, in this pandemic scenario also, the study says that the growth of vehicle is such that battery operated vehicle only itself, due to for the new registered cars, the 2/3 is battery operated vehicles in the year of 2020 globally, irrespective of the COVID pandemic situation. So you can see the need of the battery operated vehicles globally we have. And then the share of the BEVs has been significantly high in the countries like Norway, United Kingdom and France, and of course Netherlands, major share. And of course other countries are also getting a good growth. And especially to talk about India, India has increased electric bus registration by 34% to 600. It has now reached in 2020 as per the record. The 600 is the number of electric buses in the country. So although it's less compared to the global growth, but of course the roadmap is very encouraging. And the policy targets in electrification of 25% vehicle by 2024. See, all the vehicles, among them 1/4 will be the electric vehicles by 2014, and 50% of the all new buses will be battery powered. You can see the target. So even though we are having some issues here in this pandemic, but still the growth is quite evident that in the coming 10 years we are going to face a battery requirement, a huge battery requirement across the country, and of course battery manufacturing plants as well, which will stop or which will restrict our the price hike due to the other issues of customs and the other states, other countries. And see, with that, this was as of now, we have gone through the battery states. Now, the projected battery requirement scenario in electric vehicles in India by 2030, that is the most interesting thing. Under the scheme of FAME, that is a faster adoption and manufacturing of electric vehicles action plan. FAME action plan is a very famous popular action plan being taken by Indian government, is that by 3030, EV 30 at 30, it is a very buzzword now, which targets a 30% new sales share for EVs by 2030 and about 24 million of two-wheelers, 2.9 million of three-wheelers and 5.4 million of four-wheelers in the next 10 years. You see the projection, and with that, how much battery is requirement is there across the country. And by 2035, India will need to set up its own gigafactory of battery storage. In the next decade, India's annual requirement of lithium and battery storage is projected to reach 17 to 26% of the annual global production. You can see how much big consumer will be the country in coming 15 years in the perspective of battery operated vehicles. So need of battery storages, manufacturing plant, and more implementation of battery storages for electric vehicles are going to reach a good height. Now, if we classify the electric vehicles into 4 categories, you can see the projected battery storage growth See, these are the important aspects we should know, because when we will talk about the batteries for electric vehicles, its roadmap is to be made clear. Then the related challenges and research will be also discussed in this talk. So two-wheeler of electric vehicles, three-wheeler, four-wheeler, and electric buses. We have categorized the road transportation. And then we can see that mostly the four-wheeler passenger vehicles or the other vehicles are having maximum demand by 2032 in the scale of gigawatt hour. You can see it is a gigawatt hour scale. So by 2032, the cumulative battery storage requirement for the EVs in India, it's 1414 gigawatt hour. So you can see that the huge amount of storage requirement is there in the coming 10 years. And keeping that thing in mind, we need to also have the slowly battery study. And as of now, in the world, there are millions of work has been done, and the papers have been published on the battery storage characteristics, its chemical properties. But now the focus is towards the electric vehicles, how the batteries behave, which is best battery possible for the electric vehicles applications as of now. Now, batteries for EV, see, lead-acid batteries, majorly if you can classify lead-acid batteries, nickel metal halide batteries, and that is NiMH, and lithium-ion batteries, if we can consider the three categories or classifications. Then out of this, if you compare as of now at present, why lithium-ion battery is becoming more popular, and if in fact at present mostly lithium-ion battery is being used for electric vehicles, because it has several advantages over other existing battery storage technologies, which is having in the cycle life parameter aspect, if it is having 4,500 cycle life, if we go for the partial discharge, which is a depth of discharge 50%, and if you go for the full discharge, then it becomes to around 1,500 to 2,000, and still the research is going on excessively, and extensive research will lead to even more cycle life of the lithium batteries compared to the other two battery storages, which are also popular, but it was almost, it is being now it is being less adopted by the EV companies, although NiMH is still popular in some electric vehicles by some companies, but the lithium-ion battery is mostly popular by the global vehicle companies. They are adopting. And you see the cycle efficiency, DC to DC charging discharging efficiency is 80 to 90% for the lithium battery storage compared to the other battery storage. Of course, the one most important thing is that its portability and energy density, which shows part cell voltage is having for lithium-ion batteries 3.7 to 4.2 volts per cell. And of course, so the size is a bit low, and compared to that, so for the portable transportation, portable storage, the lithium batteries is having the most suitable compared to the other two batteries, other two popular batteries also. Why I'm talking about these two batteries, because these are last 10 to 15 years, these have been very popular in the vehicle aspects. And you see the charging rate, high charging rate up to 4C, C for the ampere hour capacity of the battery. So C rate is the charging terminology, and the battery high charging or fast charging is possible for these batteries. Of course, there are some challenges that we will discuss about in the upcoming slides. And you see, although the cost is a bit high compared to the lead-acid batteries and the NiMH batteries, but still research is going on to reduce the material cost of the lithium-ion batteries, because that is the most important aspect to have a more research and development is required. So for lithium-ion batteries so far is a bit costly, but of course keeping in mind the cycle life and its efficiency and its energy density as well as charging rate, the charging capacity, we need to have this kind of the battery storage. Okay, and then if you see that challenges, so this was the lithium-ion battery storage as a whole, acceptance, the reason for acceptance of lithium batteries, but we have to know some challenges here in the lithium-ion batteries when we talk about the electric vehicles. Here, there are three major aspects I will talk about. Is the stringent charging characteristics and discharging characteristics of batteries. It is stringent because it has some reason we will discuss about, and undergoes thermal runaway and explosions due to rapid temperature rise inside battery stack during irregular charging discharging of lithium-ion batteries. You see thermal runaway, we'll also explain this one through our experimentations in our BITS Pilani Hyderabad campus. We have done some experimentation studies here also, and keeping in mind EVs in mind. Although the cost of lithium-ion battery is getting reduced, as we can say that the LCOE, that is levelized cost of energy for batteries, if you talk about the upcoming 10 years, it will reduce and almost it will be very much affordable, but yet it has costly auxiliary circuitry or the support system required. Why? Because it needs a very complicated battery management system, BMS, which is the heart of the system of battery storage, for its electrical and thermal protection, because these are electrical or the stringent charging characteristics as well as the thermal protection is very much needed for this lithium-ion battery, especially because this has a very compact design and the energy density is very high. So whenever the fast charging is required, we need to always keep in mind the temperature rise. Of course, it should not reach to a level where the thermal runaway starts and the battery leads to explosion. So a couple of years back in South Korea, in Seoul, there was a lithium battery factory of, there was a mega factory of lithium batteries. 150 megawatt hour of lithium battery factory was undergone explosion because of this irregular monitoring and the irregular charging, discharging, and of course the lack of monitoring of temperature rise as well. So this leads to explosion. So we have to keep in mind while designing this kind of battery storage systems. The BESS is nothing but the complete system, which is a BESS, that is a battery energy storage system for lithium batteries. Now, as we have said, that we should look into the thermal characteristics as well as the electrical characteristics of lithium-ion batteries. So taking into account that, we should know that thermal operating range of lithium batteries, if we talk about, you can easily understand the safe zone for this working temperature, you can say, for lithium batteries 15 degrees Celsius to 35 degrees Celsius. With the green portion, this portion is the safe zone of operation, and beyond, say below the 15 degrees Celsius and above the 35 degrees Celsius, it is having battery degradation of electrochemistry, chemical reactions are there, and there will be temperature rise, means there will be the battery degradation, which will lead to the battery loss of life, and of course the explosion also it may lead to if we do not monitor it continuously. And you see that power capability through cold cranking, it is also cold cranking. Cranking mechanism is a very good research area for lithium-ion batteries who are talking about the automobiles. So automobile people for the lithium-ion batteries, they consider the cranking of this like engines and cranking of the batteries also, because in engine that is for the IC engine space vehicles, and for these battery vehicles, this battery takes place that as a heart of the system. So cranking of battery also take place, which of course we should not allow for a long time, of lower temperature range. So we need to always maintain a window of safe window of 35 degrees Celsius and 15 degrees Celsius for the charging and discharging of lithium-ion batteries. So to talk about these thermal characteristics, we have done some experimentations, and for some simulation also we have studied in our campus. That is the console-based simulation study for the thermal behavior of lithium-ion batteries. You can see it is a console multiphysics model of lithium-ion battery storage, and where you can see the temperature rise right from the outside to the inside. If you can see the blue towards the red, so red is a hot spot. It is basically corresponding to the temperature 50 degrees Celsius at most. We have done a 40 ampere charging for a 20 ampere hour battery, and of course uncontrolled your charging was there, just to show what is going to happen inside in the temperature aspects. For this console multiphysics simulation we have done, and you can see this hotspot created inside the battery. We should not allow for the long time. It will lead to explosion because it is a compact design. There is no chance to vent out this this heat if we from the inside when it is inside the stack. So we have to have some circulation inside, means air or water or other liquids. Let's see, try to have the cooling technology to mitigate those kind of thermal agitation or thermal explosion inside the lithium-ion batteries. For that, we have adopted some technology of air cooling of lithium batteries. So challenges you have seen, the thermal and the electrical. So thermal challenges can be mitigated by this kind of cooling technologies. Although this cooling technology is very popular for electric vehicle, for the lithium-ion batteries. And the airflow inlet are there through the channels. There are ducts inside the battery stack, and coolant passage is there. So we drive that cold air inside, and that extracts the heat outside. So in that way, the air cooling of lithium battery takes place. And it is the water cooling, or it's a liquid cooling, you can also say, by some small coolant or micro pump you can have from inside. There are channels, and where the inlet and outlet channels are there. So it is the battery module, as you can see. It is a schematic diagram of this. So from there, the coolant flow channel goes into that, and the coolant extract the heat from inside the stack, whichever is generated by the during the charging and discharging, and it's extract through the radiator, and it again is cooled, and further it is sent back to the battery. So in a cyclic order, it can be used to extract the heat from the battery, and keeping the considering the temperature within the limit. And this method we have recently proposed for based on the existing method of air cooling and liquid cooling in all the literatures. In 2020, towards end of 2020, we have gone through some literatures and found out that this immersion-based cooling technology for lithium-ion batteries are very much useful for especially for the electric vehicle applications, and where the battery factories are there, we should maintain always the batteries inside. So in that, you can say lithium-ion battery technology. If you can see, the battery pack is here, and through this there is a non-metallic sheet for the isolation, and there is a low conductivity coolant in a pipe we can in a container we can keep, and through the control valve there is a coolant chamber or reservoir where from this control valve with the coolant pump, as you can say micro pump, it is getting the cold water or liquid you can say inside, and it extract the heat and comes outside also. So whether there is no leakage or no short circuit inside, we have to maintain always. There is a challenge to maintain this isolation from the battery to the coolant outside. So there are thermal sensors continuously monitoring the temperature of the battery. When it is satisfactory within the limit, then we stop using this pump because it consumes power. And so we have to keep in mind optimally you have to use this power to only for the coolant purpose. Only whenever the battery temperature exceeds certain limit, we have to run this coolant pump, and accordingly we can have. So immersion-based cooling gives an effective result, which comes under the limit. And as you can see, if you can have a study of reported literature in recently, and we can see the temperature and the with respect to a study says that out of these four methods, means uncontrolled means only charging without controlling the temperature inside, then air cooling, liquid cooling, and immersion-based cooling. So it can say that the blue one, see, we can see, although the liquid cooling gives a reasonable temperature control within, as I said, 15 to 35 degrees Celsius. It is a steady state almost. We started with this temperature in order to avoid the huge data, and we have to show this portion only when the difference is more. So in that case, this area is around this color is for the liquid cooling, and the blue one, dark blue, is for the liquid immersion. We can see the best results is being obtained by the liquid immersion technique for the lithium-ion batteries. And if you don't allow, that is why the thermal protection is very much important as a part of BMS, battery management system for the lithium batteries, because uncontrolled temperature, if you can see, it can reach up to 50 degrees Celsius, which will lead to very fast, it will reach up to this temperature and it will lead to explosion because of thermal runaway. And we need to keep the temperature under control whenever the temperature tries to exceed the limit. And now this study gives us that how important the battery thermal protection for the BMS for electric vehicles. And as I said, the electrical characteristics, so stringent charging characteristics are required for this lithium battery charging profile to be maintained. For that, the green one, it is the IV characteristics. It is basically current voltage characteristics for with respect to the time. And if we go for the charging characteristics only, then green one is the general voltage. It is a very general your lithium-ion battery or popular charging technology, but there are some issues. This green one is having this battery voltage where you have to maintain after certain limit. You have to maintain the voltage to the constant voltage mode, and before that constant current mode. Although it is said constant current, but it is not a constant current. We have to have some modifications based on the stages and voltage and battery state of charge, also state of health. So here the soft charging initially to avoid the high charging inside current battery, and also inside the battery thermal agitation should not be very high initially, as the battery is assuming it is discharged. So we need to have a little bit of small current of soft charging techniques, C/10 or C20 sometimes also, and then directly we go to the bulk charging phase. Bulk charging phase, we have this phase of maximum power transfer can be possible also if you go for the solar applications as well. And then we talk about this constant voltage mode, where the current goes down up to a certain limit until the voltage reaches the complete charging voltage of the lithium-ion batteries. So as I said, per cell voltage is 3.7 to 4.2. We are considering that kind of voltage level, and per cell, per C means per cell. So in a single cell voltage, it is a battery charging characteristics, and similarly, you can go for the battery stack as well. If you go on series, same current profile will be maintained and the voltage also will be scaled up. So accordingly, we have to maintain the charging profile. There are depending on the your device, depending on, you can say, the electric vehicle charging process, there are pulse charging also sometimes required towards the end. Instead of having constant, we can have the pulse charging or required also, depending on the load conditions. For the electric vehicle point of view, there are a chance of battery drainage faster, because the depending on the road, also even the surface of the road and the speed of the vehicles, the torque required by the motors, those are all powered by the vehicle, the batteries, as well as the vehicle inside electronics, and of course the air conditioning system, HVAC system, that is called the HVAC, heating, ventilation and air conditioning system. That everything is powered by the battery for a BEV, battery operated vehicles we are talking about. So for those issues, battery undergoes a random discharge, and of course for the battery, it needs to always be monitored. That is why BMS is required, as the temperature is a major concern for the lithium-ion batteries. We'll talk about that also in the control box of the BMS in the upcoming slides. And of course, the charging issues will be also discussed in the charging station part. Let's see, with that, we are having this subsystem of BESS, that is the battery energy storage system as a whole. It includes, let's say, battery pack are there in series or parallel, depending on the current voltage requirement. And this battery pack, along with the BMS, there is a micro contents of BMS every in all the strings. It may be, or it may be central BMS. There might be two patterns of the BMS available in the market, and the research is still going on to optimize the BMS. And this kind of BMS, of course, it involves major components of the state of charge prediction, state of health prediction, and real-time monitoring of battery temperature. And for the charging discharging, proper charging discharging, we need a converter electronics part for bidirectional power flow from the source to the battery and battery to the loads. And here the supervisory control and SCADA system is there, which of course a centralized controller which controls the entire the battery operating the interfacing system, the converters, battery inside BMS part, and of course the your optimized power flow from the battery and to the battery. So this everything is monitored from the central controller. The entire system calls the BESS. So battery is a unit only, and this battery is having this having electronics part. It has having the BMS controller part. It has having the intelligent systems part, and also of course the entire chemical system monitoring part. So the entire BESS is a total system under this. These are the subsystems we have to monitor. And of course, for EV's point of view, we need to have design the BESS in such a way that the battery life gets unaffected, of course less affected, we can say practically, and of course the charging discharging happens within the limit of temperature. And as I said, the BMS is having a battery management system for EVs. Especially, we can talk about the EVs also. We can say these are the four major components we need to talk about this BMS, where the state of charge estimation, dynamic internal impedance estimation, and battery temperature controller, which leads to thermal aging if you do not talk about it. Then self-discharge rate, which is a very significant for many batteries, and as a result, if you keep on in idle condition, of course, after having a charge, it gives a self-discharge after a couple of days or a couple of hours of without or non-operation zone. We have experimentally seen those results in laboratory, and that that battery undergoes a self-discharge, which has to be also catered by the charge controller, because that, of course, lowers down the voltage, which actually was supposed to be. Accordingly, incomplete charging might take place every time due to the self-discharge effect if we do not properly estimate it. So there are four things: SOC estimation, as it is an electrochemical estimation process, and dynamic internal impedance, it is also electrochemical internal impedance of the battery, which leads to the battery potential drop, which if we have to monitor it. Also, this temperature controller, it is also important thing, as we have also we have just discussed a couple of slides back, how the temperature of battery needs to be monitored all the time. So the BMS includes majorly these four components we have to talk about. It onboard. It is an onboard your controller is required for that in the vehicles. You see, talking about this BMS operation inside the vehicle, how it is behave, how it is the architecture of this. It is a block diagram approach, you can say. So the BMS is a controller part, and from there the battery is a bidirectional flow, and sensors are there, and battery needs to power the loads, converters for the other accessories, and the motors also for this driving system. Power converter is required, inverter is required. So DC to AC, mostly the PMDC or now switch reluctance motors are also getting used in addition to the induction motors. For the EVs, especially these are being popular motors for EVs. As we know, drives is a very separate system to study, so we won't talk about that much. We will go for the battery only. And now this battery is also, as I said, that HVAC system, communication system, and onboard electronic system. We have to maintain the power from the battery itself. So the BMS plays an important role inside an onboard operation of electric vehicles, and of course the drive system as well. So to talk a little bit more about this master-slave communication in the BMS, it is the most important part because communication has to be in almost real time, in micro to milliseconds. And of course, we should not make any delay, and those steps we need to monitor. There's a CAN-bus system. It is called this control area network. There is a CAN-bus system communication is taking place inside this BMS architecture, where the master and slave layers are there. We need to see the battery pack. There are in the battery pack, there is a temperature sensing mechanism, there is a current and voltage sensing mechanism. Other majorly these three are the sensing mechanism, and they are communicated through the master-slave communication technology, and through that in real-time system this communication makes us between the loads and the battery as well as the other existing loads inside the vehicle. And now the point is this communication system is a separate area of research again, because how to optimize the communication system, how to make it low cost, how to make it smart communication based on the IoT based. Nowadays it is a IoT based communications techniques are being adopted largely, and of course there is a low cost system everywhere. It is you know it is adopted and encouraged to implement this BMS architecture satisfactorily for the communication systems. And see, if we talk about this as a whole, if we can summarize as a whole, now we have seen the growth of the electric vehicles in globally as well as in India. Then we can see the battery storage growth, and then the implementation of batteries. To implement the batteries, lithium-ion battery is the most accepted battery as of now, but it faces the challenges, and how to mitigate those challenges inside the vehicle we have talked about as of now. But we have not discussed this thing, that is the fate of the battery systems in the EVs after the first life of end. What does it mean? You see, the first life is nothing but when after the manufacturing of the batteries, the first choice is for the vehicles, electric vehicles and transportations. The transportation systems and the telecom sectors, these are the first choice, and where we can see that after the first life is towards end, how to or doing to scrap it, because there is a environmental aspects. We cannot scrap this kind of highly toxic material of lithium in the atmosphere. In a bare atmosphere, we cannot scrap this material. So we need to recycle. There must be a recycling mechanism in these batteries in the by industries. So we will talk about this also. See, the car scrapped, if we can say, from there the battery recovered, means the remaining portion, remaining life, or you can say remaining useful life of the battery. And there is a two category. One is exhausted totally, another is still a viable condition. So in totally exhausted condition, we can see there is no other options. Then the battery or car manufacturers, they are responsible for recycling it. So recycling factory, it is already there. In India, it is slowly getting developed based on the demand, because when it will be, say, as we can see, the projection coming 10 to 15 years of the projection of the battery development or the growth of the battery storage in coming 20-30 years, then when the batteries, it has a finite life. The lithium-ion batteries 4 to 5 years. After that, it has to be replaced, or there should be some replacement. So do we need to scrap it? We should not scrap. We can recycle or reuse it. Of course, it may not be it is regained as the same capacity. We may not use for the electric vehicles only. We may use for the other power applications of those second life batteries. Okay. So for that, it is a recycling is processed. And then the viable batteries, you see, viable condition, we come to the workshop for repurposing. It is a very interesting thing, is the recycling and repurposing. Repurpose means we are not totally disassembling the system. We are having those internal material, we are disassembling it, and we are taking those electrodes and other materials to form to make a new battery pack. That is a you can say battery stack can be reformed, but recycling is totally right from the scratch. We will, after demolishing the system right from the scratch, from the material aspect, we are building the battery again. And these repurposing of, workshops are also available globally. You can see in China and in US, there are a lot of companies are available now who are working extensively on this repurposing and recycling of batteries, because nowadays globally electric vehicle growth is exponentially becoming high, and coming 10 to 15, 20 years, keeping the scrap material in mind, we need to be ready with that, because environment, because of carbon emission mitigation, we are using batteries, and these batteries will again in turn have the environmental hazards. So we have to also be ready by ourselves that what is the fate of this battery after a couple of years, when at the time of disposal. Now, these repurposed batteries, they are used for the renewable energy applications and the grid scale applications. That is the point of why I'm investing more time on this slide, is that see the fresh batteries, they are used for the electric vehicles, and after a couple of years, when the first life gets ended, then we can repurpose or recycle depending on the battery condition. And then for the repurposed batteries, are after some reformation, we can use it as a second life. Recharge, we can recharge the battery, and you can say revive the battery, you can say, and for the renewable energy applications and grid scale applications, we can use it for the second life of the battery. And after even exhaustion of that, we can get back to the recycling for the fresh battery for the new applications. So in this way, the battery flow of the fate of the batteries after the first life can be foreseen. Now, so far I have discussed about the electric vehicles in the running conditions, means under the vehicle only. But vehicle is not a vehicle only; it has to be accounted with the charging stations. So we need to have, and batteries again are the key factor for the charging stations. So let's talk about some batteries for the charging stations as well. And see, if we study as a background, as we have done, for the ratio of public charging stations per electric vehicle stock by the country-wise in 2020 or till 2020, what was there? You see, EVSE is nothing but the electric vehicle supply equipment, and per electric vehicle, what is the ratio? You see other countries, and you see here the ratio is very small, means the charging station means basically the supply equipment or charging infrastructures. So charging infrastructure is really less compared to the how much number of vehicles available in India. So now, compared to considering that in mind, we need to have more focus also simultaneously in the EV charging stations. So as the charging stations will be implemented, you see the low ratio gives us that idea that how much potential it has in the coming 10 to 15 years with the growth of the batteries and the vehicle usage. So definitely in the ratio, we have to maintain and we have to improve the ratio, and to implement more charging stations we need to have. So now for that, more batteries are required. See, it is a glimpse of EV charging station being implemented. I won't take the names, and definitely the companies are with the government, the PSUs also, they are now tying up with all the petrol pumps. They are also accompanied by electric vehicle charging stations now, and separate charging stations are also being adopted rural areas as well as urban areas and the roadsides. So here the generalized layout of EV charging stations. There I have seen the talks about these charging stations are there in the upcoming events, also in this upcoming sub events of this EV theme of this workshop. And here we can see that I won't talk about this charging station infrastructure and its optimization or allocation, but I will talk about the battery storage suitable for these charging stations, which we can think of in the upcoming areas. Because in this FDP, I can see that many researchers, it will be helpful for you if you can discuss this thing here. And I will expect some questions as well at the end. You see here the renewable energy fate system. We are discussing about the grid dependency and also grid independency, thinking that in mind. Renewable energy fate system, and of course the grid is also there. So grid connected and off-grid system charging stations. So sometimes vehicle to grid and grid to vehicle is also V2G and G2V are the two major aspects of research nowadays. It means how optimally vehicle can be fed to the vehicle can during the parking or when it is at rest, it can contribute to the grid also for the charged battery. How to balance? There are some aspects of power sectors and the distribution grids. We have the electrical aspects or the frequency aspects and the stability aspect as well. So there is a V2G, and sometimes G2V is also, it is very popular, grid charging. And of course, the renewable based charging is also nowadays getting popular to promote the green transportation as well as the green energy. And for this battery storage, we are having this off-grid charging station and on-grid charging stations. So it is a generic infrastructure or the schematic of the EV charging stations. Now, the major type of the EV charging station, why we should talk about the batteries more in this EV charging station, because there are majorly 4 categories so far in the EV charging stations, depending on the grid connectivity. That is the on-grid or only grid connected. It is almost popular in all the sectors. Grid plus renewable to promote the green energy. Then grid plus renewable plus storage, including the batteries, fuel cell, supercapacitor. Mostly the stationary storage we will talk about here, not the portable storage. And off-grid renewable energy plus storage. There is no grid. In rural sectors, because in electric vehicles, 3-wheeler auto rickshaws are there. Those are having electric e-rickshaws. There are, or e-auto rickshaws are there in all the, especially in India, they are in rural countries, rural states. They are using the 3-wheeler EVs extensively nowadays, and they are mostly, the grid charging is there. And sometimes if you want to promote, then there are off-grid system also, standalone EV like booths of charging stations. They are getting now decentralized base, they are getting designed and implemented, small scales. And of course, these are including this storage plus off-grid renewable energy. So these are the 4 categories inside. And if you talk about the batteries now, because today's talk is all about batteries, I won't talk much about that grid connectivity and the grid balancing also. These are the special area of research, a separate area of research, those are. But we will talk about the batteries for electric vehicles, charging station now. And to talk about that, we should know that the charging pattern for the electric vehicles in the charging infrastructure. That is residential charging with AC supply, workplace and public charging with AC supply, DC fast charging with DC power supply sometimes required. So there are level 1, level 2, level 3 different names where fast charging, extra fast, ultra fast, super fast chargings are there. Also sometimes medium charging is also there. So there are different level of chargings are available for the depending on the vehicle scale. And we need to have a proper battery, and for that proper battery management system, BMS for that. So if we talk about the batteries for charging stations, if we, as we are saying that it is a stationary storage, if we can talk about the stationary storage, then stationary storage means definitely we have to have a scaled up value, because the charging station, there is no restriction for that portability or having a very high energy density. But of course, durability is important, the life cycle is important, and of course the integration from the renewable energy sources, as well as the charging pattern or permissibility of the charging levels, because fast chargings are required sometimes. So definitely from the battery it should be discharged. So we need to think of those batteries. And for that, one most popular battery already all over the world as of now in EV charging station as well as EVs are being used, as I said, lithium-ion batteries. But I will focus on a little bit more and other battery system as well, which gives us in the potential aspect, if we can think of, in the coming few years, it is getting extensively being used in megawatt hour, especially in large scale for the renewable energy applications. And that is, you can see, if we talk about the 2 specific batteries here, one is the lithium-ion batteries, already established technology, and another is the VRFB system, that is the vanadium redox flow battery system, which is a flow battery and which is having, although low energy density compared to the lithium-ion battery, you can see the part cell voltage, but the 2 major advantages it has is its highest cycle life as of now in the laboratory scale as per implemented. Of course, in the field scale also it is getting implemented now in many countries in Europe mostly, and of course slowly when we talk about the stationary charging, and of course the cost is also getting reduced for the vanadium ions, your material, because from the fly ash content from the thermal power plants, and there is a huge amount of this is source of vanadium as a your material, and we can say we have to extract. The technology is also being adopted to extract those your fly ash content based vanadium, and to use those into the VRFB system to manufacture the VRFB stack. And you see this battery we are talking about, especially it has the battery life can be made even longer. You see the 13,000 plus cycle is there. So which is approximately equal to or you can say approximately close to the life of solar power plants. We are having the generation guarantee of solar power plants. Literature says that the solar power plants are having almost equal life cycle for these vanadium rare earth batteries. And as a result, it is quite encouraging to use for the stationary storages, not for the electric vehicle portable operations. Portable operations, lithium-ion batteries are sufficient enough as of now, but for the stationary storage, we can also think of, in addition to these lithium-ion batteries, we can have this potential of vanadium rare earth batteries in our hand, and which is having 13,000 plus cycles. It is very much useful to avoid this battery, the scrapping of the batteries, or you can say after a few years we have to renovate the system. There is no need, because it has scalability of power and energy capacity, because its power capacity depends on the battery stack, I will show, and the energy capacity depends on the battery electrolyte volume. So those can be independently scalable, and whenever which kind of load or you can say capacity is required, we can add more electrolyte or add more stack in series or depending on the configuration to increase the battery capacity. So there is no need to totally renovate the system. And in off-grid and or on-grid EV charging stations, lithium battery is suitable for the fast charging with relatively low cost. As of now, whole world is using lithium batteries for the fast charging, because there is a capacity of lithium batteries because of its portability and high energy density. But that still remains, the challenge remains in the design of BMS, specifically a complex BMS for the lithium batteries. But for the VRFB, slowly in the upcoming slides, we will learn how VRFB is going to be more suitable for lithium rather than lithium batteries in the upcoming years for the stationary charging stations, stationary charging applications. VRFB can also be considered for the very long life cycle, as I said, close to 17 to 18 years, which is close to a solar power plant life, and its scalability of power energy capacity where the grid is unstable or renewable energy sources are integrated. But VRFB is suitable for the stationary, as I said. It cannot be used for the portable storage because it has a bulk structure because of this low energy density. Now, with this knowledge, let me just briefly show the working principle of VRFB, because many of us might not know that exact working principle, why we should go for this battery in the upcoming stationary storage applications in the coming 10-15 years, although it has been started in the other countries. Now, vanadium rare earth batteries, and we are thinking of slowly towards the EV charging stations, as it is having the stationary applications scope, as well as we are promoting towards green transportation and promoting towards green environment. So rather, let's operate from the thermal power operated grids and more operate to the renewable energy fed system where the storage is a must for the balancing and stability. So this kind of long life storage batteries are very much encouraging in the coming few years. See, this kind of this is the very basic thing where this box is the battery stack, and inside there is a membrane which separates the two sides, two half cells. It is a proton exchange membrane made of naphions, and there are two graphite electrodes, which is a anode and cathode, and through you see there are two electrolyte pumps, two electrolyte tanks, okay, where the vanadium ions, they are by electrolysis process, they are separated and making anodite and cathodite, means plus and minus side, and from the micro pumps, it is you can say one self consumption is there for the micro pump. But in the other way, we need not to say cost much more, like lithium batteries is being consuming much cost in the BMS. This battery BMS is very simple because it has an exposed structure, so temperature rise is not that much effective. Yes, so definitely one good question, I will talk about that. Okay, better to just have a small address to the question which appeared in the screen. I have seen the thermal power plants, they are now almost shutting down globally by say coming 10, 15, 20 years. But the point is, as I am talking about the fly ash content, how or where can we have this vanadium ions, vanadium material? So extracting this vanadium material from the fly ash content is a now new technology. But of course, other than this fly ash content, it has many, it is rare earth material, and these are available also, like lithium material is available. Vanadium is also available in many countries. But of course, in the countries like India, we can see if we want to reduce the cost in our in-house productions, then we are talking about this fly ash content. And of course, if they are going to shut down, completely shut down won't be possible, because in countries like India, especially in coming 50 years also, as long as coal is there, it will be run, but definitely it will be scaled down and replaced, getting say backed up by those renewable energy, more and more implementation of solar energy and wind energy. of course, with that, we can have this battery storage, your material availability will be there. So thinking of in my mind, of course, there is the fly ash is not the only source. We are having, it is a viable source in the Indian scenario I am talking about. But for the globally, people are using from other sources also for the vanadium extraction. Now, let me just talk about these two cases. There are two micro pumps, and micro pumps with 3 to 4% of the total system loss it consumes. It is definitely a consumption, but you see in the long run, if you think of a long run battery storage, then it is definitely for a short-term goal, we cannot see the profit. But in the long-term goal, we have seen the significant profit in case of the your vanadium redox battery storage compared to other battery storages. If we talk about the LCOE, means levelized cost of energy of that. So through this pump, the both side electrolyte is circulated and the charging takes place. If we have our external power supply to the stack, so from the solar or from the grid, whatever it may be, and DC power supply. And the basic important thing is that high charging current is possible because it is exposed structure, although taking much more space. That's why in stationary storage it is more important. And for that, you can see this high current charging is also possible in this case, as well as the electrolyte not only acts as a your reaction content, but also it not only acts as a catalyst, you can say, but also it contains it acts as a coolant as well, because if we can circulate this liquid from here, this vanadium and sulfuric acid acidic medium, the pH is of course below 5, it is highly acidic. So 3:1 ratio H2SO4 and the vanadium is mixed to prepare this electrolyte, and this circulated electrolyte flow gives us the idea of extracting the temperature from the stack to the tank every time. So we don't need extra thermal management system in the BMS. It is the advantage of this battery, which is not there in the lithium-ion battery storage. And it is a charging discharging basic reaction. That is why it is called a redox flow battery, because reduction, oxidation both takes place during charging discharging, and vice versa. It is a reversible chemical reaction. And to talk about this interfacing, you see this is the battery storage information now. And now to talk about this interfacing part, if we can think of interfacing, you see we have developed a couple of years back this kind of interfacing device from solar, where it is a schematic of that. It is reported in a Journal of Energy Conversion Management in 2018 of our research group, and where we discussed about where we have demonstrated the charging of VRFB storage from solar, but only challenge compared to that other battery storage is the real-time flow rate control, because flow rate is the main source of, you can say, reaction acceleration as well as the coolant in this battery. So we need to have real-time flow rate controller in the battery simultaneously, apart from this so-called MPPT charge controllers and other your battery charge controller techniques, and maintaining charging profile as well. We can have a constant charging current. There is no such stringent characteristic required like lithium-ion batteries. So that is also stationary storage, or that is permissible. In that case, there is no such stringent charging characteristics required. And at the same time, only you have to look after the flow rate control all the time, because it circulates all around the battery storage whenever it is charging, discharging is taking place. And this flow rate also not only accelerates the or impacts the charging profile, the charging operations and discharging operations, but also it acts as a coolant. So this was a developed system, and you see the real system is here. If you can see a better flavor of it, it was also reported to the same Journal of Energy Conversion Management. You can see also from there in the literature. See, this is the real system setup we had, and here you can see these two electrolyte drums are there. It is there. It is placed in IIEST Shivpur. It is there. And in the lab, in the renewable energy lab, we have this setup of 6 kilowatt-hour lab scale vanadium battery system we had, and where this stack it is a stack, and both sides there are electrolyte tanks, and through the pressure sensors and temperature sensors, continuously we keep on monitoring the temperatures and of course the flow rate control. And there are two pumps, micro pumps are there for this. Let me tell you one thing, that 1 kilowatt 6 hour battery. So for the 6 hour it can discharge if it is fully charged, and 20 cells were there, each 1.6 volts, total 32 volts were there. So around 50 ampere charging we could permit at a time. So it's a high charging current, you can say. So this 1 kilowatt system we had, the two pump consumption was 45 watts only. So 1 kilowatt system is 1000 watt, we have the 45 watts only as a consumption under the full load condition, not always. That is also remembered. So this we can easily accept if the performance is better than the other batteries. And this was the developed charge controller system from our end, where the DSP based charge controller we have designed and developed and demonstrated as well with the 3 kilowatt solar power plant. So to talk about more, because we need to know more on this battery storage if we are thinking of really in the upcoming storage in this stationary charging process for these batteries of vanadium redox batteries. So it is a typical charging, it is a under say 7 a.m. to 11 a.m. we had a real demonstration. I would like to discuss a little bit more on this also for your interest. Those who are interested, they can contact me later as well for some collaboration or some research queries regarding this if you are interested. So let me tell you quickly this thing that 400 to this 800 around the watt per meter square irradiance profile was there under this morning session. We had a charging and in a sunny day, and this is the charging profile, current profile of the battery, because see we have had MPPT charging, 3-stage constant current constant voltage charging. There also a 3-stage charging with bulk charging phase where the MPPT is adopted. So we had the extra energy we can extract to the battery, and we can do it because VRFB system, you do not need to have a compact structure, as well as the temperature rise is not that stringent, unlike lithium-ion batteries. So it is a typical voltage profile after the charging of under different charging techniques we have gone through, an experiment done on the 6 kilowatt hour VRFB storage system. So vanadium redox battery storage system undergoes this kind of charging. As a result, as I said, a thermal management system we need to keep in mind, but that is of course not that stringent or in real time. You see, only flow rate control can give us the acceleration, or you can say the effect on charging discharging system as well as the cooling system, because that is the only source of flow inside the batteries. And now you see here, it is a very basic structure of control system of thermal management system. I won't go to the details of this because it is a separate study of how the pump, you see, as you have seen the two pumps. So only way, or you can say a simplest way to control this flow rate is by controlling the pumps through some variable frequency drive outside, because these are AC pumps, single phase AC pumps. So those pumps can be controlled, and real-time temperature sensor is there on the stack. They are sensed, and with the reference, whichever is, let's say for example, literature says that the vanadium redox batteries having 5 degree to 45 degrees Celsius of temperature range. Of course, it is more than the lithium-ion battery storage, as it is the exposed structure. So there is a chance of venting out the temperature, and also the internal stack temperature you can release to the tank in a cyclic manner by the help of flow of electrolyte. So optimization on the flow of electrolyte is very much required to avoid the temperature rise inside the batteries. And one more aspect of this optimization, because when you are talking about the battery system, you should think of the battery system performance, not in terms of temperature only, but also the losses. So in this vanadium redox batteries, it is having this loss of I square R loss, and this resistance, internal resistance, depends on the flow rate. If we have experimentally seen in our lab, it is that, and reported in the Journal of Power Source as well as the Applied Energy Elsevier, in this thermal management system, we have examined that the internal resistance gets varied under the impact of flow rate variation. For more flow rate, if we talk about, then less resistance is getting less internal resistance. And if you talk about the less flow rate, it is getting more internal resistance. That is a chemical property. We won't talk about the chemical properties here, but it's an observation I need to share with you. That so apparently it looks like that we should maintain the high flow rate always to have this low resistance in the battery stack. But I mean, in order to get the low power loss. But the issue is, if we want to have that, then the power consumption in the pumps will also be increased. So to optimize in between that, we need to have the temperature control as well as the loss control together by the optimization of flow rate. So between the highest flow rate and the lowest flow rate, there must be an optimal point which we have to track always based on the battery health. So optimal flow rate and temperature control of VRFB storage, as I can say, this is optimal flow rate we have achieved. For here, you see that over the state of charge range, say a charging process, 0% to 100%. Under that, 10% to 90% we have allowed for the safe charging zone. Under different current levels of charging, you see the fast charging is possible. And in the lab scale of 1 kilowatt, same 1 kilowatt battery we have taken into account in the lab scale research for this, because when you talk about this vanadium and your redox batteries, then we have to have all possible experimentation done before you go to the field. So now this variation of with the state of charge, each and every state of charge has an optimal point, and this optimal point is identified based on the temperature rise inside the battery as well as the loss. So as a whole, you see the optimal point if we can have under the ambient temperature of 30 degrees Celsius in Indian context mostly. If we see, say, constant flow rate, if you do not optimize, means if you do not keep on vary, if we have a constant flow rate in the battery, then after some time it will, if it is not that much high, then it will increase it up to a certain limit, and 40 degrees Celsius, as we have seen, the 45 is the barrier of thermal explosion. You can say not explosion, basically it is a thermal runaway after 45 degrees Celsius in this case. So that for that case we need to have a restriction here, and as a result battery thermal shutdown will occur and it will be incomplete charging. You can see 60% it will be finished by charging, but of course it is incomplete charging. So we should not allow irregular charging, and as a result we need to monitor this flow rate. So for flow rate, if we monitor, as a result of the optimized flow rate, we can achieve the temperature under control as well as the losses also in the optimized form. So both we can control with the central flow rate control. That is the advantage of these batteries, apart from the scalability and of course longer cycle life. So controlling is a bit easier. And so this is the range, the reason for adopting, or you can say slowly, if we try towards this stationary storage applications for the charging stations, because you know that in India you have seen already that ratio is very small compared to the EVs and the charging infrastructures. So in the coming years, considering in mind infrastructures, if we consider, then definitely we have to keep in mind the battery is suitable for those applications, where the vanadium redox battery is an upcoming storage solution which can be integrated majorly in the renewable energy sectors for the larger scales, kilowatt to megawatt hour. And of course we can also mitigate those chances of lithium-ion batteries, that explosion and thermal stringent characteristics, those also we can get rid of, because anyway in electric vehicles lithium batteries are being used. We cannot replace immediately those things, but we can also think about there are different technology, battery swapping, there are battery multiple or hybrid storage, supercapacitor, fuel cell battery storage, all are there in the charging stations. These are being still under development. So this battery storage, vanadium redox battery storage, you can think of as a charging station alternative in the upcoming years. So in a nutshell, if we can have this overall discussion, the batteries are going to be the key players to promote the sustainable transportation, which is nothing but leading to EVs, and then focusing on the government policies and of EVs and upcoming demand. The countries like India should be give more emphasis on the indigenous battery, as I said, the indigenous battery, including BESS in the control system for manufacturing plants to optimize the overall system cost. And for that, the in-house material, right from the material, we should not also, we have to develop our in-house manufacturing plant for the batteries. Although there are some manufacturing plants are being now, they are started last 5 to 10 years, but still we have to scale up this capacity of manufacturing, and of course to meet the demand in the upcoming few years. And of course for the EV charging stations, more renewables we should promote to reduce the carbon emission. And if once we are talking about the solar and wind and these intermittent sources of energy and the suitable battery storage for those systems, considering the longer life and the scalability of the battery storage, the vanadium redox battery storage can be a potential solution for those EV charging stations in addition to the existing lithium-ion batteries. So this is all about my discussion on batteries, especially on vehicles. I hope it is helpful, and I would be happy to answer some or interact some of you if you have any questions and queries. Thank you very much. And you can also contact me in this email ID I have. You can note down, and you can contact me in future also for the research queries or collaborations. It is all open. Thank you very much.
Thank you so much, sir, for your informative.
I finished early because I was thinking of running behind time, but it's so at least to
that's okay.
Much time.
So audience are welcome to ask questions.
Okay,
you may
so
interact.
let me
you have given
minimize the screen, then you can understand.
permission to unmute yourself. Yeah. Yes. Sir. So you may unmute yourself, participants. You may unmute yourself, and you can ask question, or you may put your question in chat box.
Let me enlarge the screen. Actually, I cannot do it from here. What else? What can we do? I need to see the question actually.
Okay, okay. You can go right side, participant side. The
Right?
chat box is there. Yes.
I think this one.
But we can see in chat box there is no question yet.
Okay. No, but during presentation there are some questions I can see. Yeah.
Okay. Okay, you check if you
And
also because that's okay. One question is there.
let me see. Actually, I cannot
If
see
we
here.
first charge the are you able to see, sir?
No, not yet.
One question.
Just not yet.
Yeah, just you check the chat box.
Yes.
Are you able to open?
Actually, in Webex, not
Right side. Just just you.
Okay.
Stop sharing, then
Yes.
you will find. Okay, actually, your cursor is above to that. Yeah.
Yes. Thank you.
Will
Thank you.
get
Yeah.
it.
Now I can see. Let me see the chat box. See if there is any question by this time.
Yes. Yeah.
To say restrict the internet consumption, let me stop the video as well. Yes, there are some questions. Okay, so maybe Professor P. Saini Ranjan Kumar. Yes, thermal power plants are being closed by 2030, but the point is that in talking about the future of this VRFB, it is not the, as I said, only source for this fly ash content. So as a result, we can see that there are other alternate courses of source, because in the other countries, people are not depending on the thermal power plants, but still they are thinking of the battery storage on vanadium. So we are, and in India, at least in the coming many years, at least significant 2050 till we are having not at all a zero state of thermal power plant. Of course, they are planning, but definitely it is not possible to replace everything by renewable energy, right? Yeah. So next question is, other than long life cycle, what are other advantages? Yes. So I have discussed, maybe by that time you have gone through, I guess. So it has a longer life cycle. It has scalability, as I said. I have shown the picture of there that it can be scaled up and modified based on the requirements of the stack and the electrolyte. So by adding more electrolyte in the tank, it increases the energy capacity of the battery, and by adding more stack or more stack, I can say cells to the stack, you can increase the power capacity. So power capacity depends on the area of the stack, and energy capacity depends on the volume of the electrolyte. So these are, unlike the other batteries, these are the advantage of the lithium-ion batteries we can think of. And third question from, if we fast charge the battery at level 3, DC charging, what will the effect on the battery life? Very good question. See, of course, the fast charging, if we talk about the lithium batteries as of now, existing technology, rapidly being used, in that case, we need to have a specific battery management system, keeping in mind thermal agitation, of course, the limit of the temperature rise inside the battery. And as we know that level 3 means, of course, the sometimes ultra fast charging are also required, now established technologically, and they need proper protection of the battery storage. Of course, continuous monitoring of the battery thermal management system, how it is working, as well as battery state of health. So definitely it is going to impact from the normal charging state, because that current rating level you are making high. So definitely thermal temperature rise will be also very high. So okay, same questions maybe twice asked. Okay, so any other question, you can unmute also. I'll be happy to interact with you.
Excuse me, sir.
Yeah, please.
So I have a question. In terms of energy storage for EV charging stations, will it be possible for like using an alternative energy storage system in place of battery systems, like for liquid air energy storage systems and like that, sir?
Yes, of course. See, here we are talking about the battery storage only. That's why I have focused on the battery storage part. But of course, as you can see that the fuel cell supercapacitor are also being used as hybrid storage in addition to the battery storage, where the flow batteries also are coming in the picture. Similarly, we can use the other storage capacities also, like you can say for EV battery systems now, sometimes the storage of fuel cell from the rural areas, if you can think of the bio waste. So bio waste, or it's a waste to energy. From there, the available municipality solid waste, and of course the other residential waste, which are biodegradable, which we can generate hydrogen, and from there we can fit to the fuel cells and act as a storage. So of course this hydrogen generation and its treatment is a challenging technology. Also needs to, and now it is underdeveloped. Still it is getting some stability issues, and there is continuous during the process of hydrogen generation there is also carbon dioxide emission, and we can recycle by using methanation further, and then further hydrogen generation. So the process is still going on of the other storages. Definitely there is a potential, and we need to know, or such kind of storage we need to choose which is having less impact on the environment, and we can use the environmental parameters or available parameters or abundant sources around us to generate those power for the sources for the storage. So with that, fuel cells are very interesting storage. So I think your questions I could address.
Yes, sir. Thank you very much, sir.
Thank you. So maybe some other questions are there. Anything about shortage of semiconductor materials? Yes, of course. See, in that case, this is, although it's not the platform to talk about this semiconductor device, but still I should say that because of the rapid technological development of and the miniaturization of semiconductor devices nowadays for the controllers and converters, now we are not thinking much of this for the batteries for these semiconductor materials, but you know, the scrap, you can say this disposal of this after some years of the semiconductor devices, now whole world it is now very much worried with this, and technology is being also developed how to optimally dispose or how to optimally recycle sometimes if possible, and how to reuse those kind of semiconductor materials after a certain year of usage of whether it is for electric vehicles, whether it's for telecom sectors, whether it's for other electronic operation systems. Semiconductor in this case, I guess you mean the electronics part of the this battery storage, and shortage in the sense we can see that life cycle, as we can say, of course it is a finite life, but the disposal again it is a hazardous to environment, so we have to think of that also. And automobile battery and inverter battery, yes, very good fundamental question. For the automobile battery and inverter batteries, you know there are different batteries of gel batteries, there are dry cell batteries, wet cell batteries. And so in inverter batteries, if we think of then in our households, we normally, there are flooded batteries, there are VRLA batteries. Mostly we are using these inverters as of now, lead acid batteries, because these are low cost for household. It is viable operations is possible, and of course we need to replace after a few years. As of now, as the lithium batteries cost is still high, and it is only used for the your very much needed technological advanced applications like automobile sectors and telecom sectors, other renewable energy operation sectors. But for the household lithium inverter batteries, mostly in commercially available, they are using lead acid batteries, and still research is going on. Companies like Excite, they are also in India, they are having extensive research on how to improve the capacity or remain useful life of the lead acid batteries, how to improve the life cycle of the batteries, how to restrict the degradation, fast degradation of the lithium of the lead acid batteries. There are different areas of lead acid battery research nowadays for the inverter batteries, we can say. And this automobile batteries, these are of course the your high it should allow the fast discharging and fast charging. So definitely it is a different manufactured battery, and although electrochemistry is same, but of course the life cycle, number one, number two is how much capacity it should allow for charging, discharging, how much remaining useful life it is, and of course the control scheme, because battery, we are not thinking of battery only. When we are thinking of battery, it should be thought of BESS, because battery energy storage system as a whole. So that is the aspect, or you can say focus point for the batteries. So yes, so any other interesting questions? I can see some good questions from relevant questions rather in the common field. If you can ask me further on EVs, batteries for charging stations and EVs also, we'll be happy to interact. So if any other questions are there or not, then we can. Although I have finished earlier, thinking of there will be interactive sessions after this.
Yes, sir.
Yeah.
It's okay, sir. Anything else? Any more questions from audience side?
I think they are done. So
Yes.
we can wait still for a while. As
Yeah,
the session has not yet.
So 3 minutes, yeah.
Yeah. And regarding this, if you have some research queries also, you can mail to me. I have already provided my email ID. They are mentioned. And regarding the battery storage applications.
You can type your mail ID in your
In the chat box,
email
right?
chat box. Yes, sir.
Yes,
That
yes,
will be
that is
more
also
better.
possible. Correct.
Yeah. So everyone can keep it with
Interact
them.
later on. If not, question might not come in mind. Later on, you can also ask me. We can interact. I guess it is visible, that email ID in the chat box.
Yes, sir. Yes, sir. It is visible.
Okay, if there is no further question, then we can.
Yes. Yes. Okay. Thank you so much, sir, for your nice talk. Very informative, and I hope that the audience will get benefited from your ideas, from your work, what you have expressed here. So thank you so much, sir, for accepting my request to be a speaker for the very informative session. I hope we will be doing such activities in later on also. So thank you so much, sir. This is for you, a token of appreciation. Thank you so much once again, sir.
Thank you very much, Dr. Kundan, and thank you the audience for patiently listening to me what I discussed. And I guess some questions also might come in your mind later on if you think of it. And you can also anyway, anytime you can send me emails. We will interact over phone and email also. Thank you very much. Thank you for the session.
Thank you.
Thanks.
Thank you so much, sir.
Yeah, thank you.
You may
So
leave
should
now.
I log out now?
Yeah.
Yeah. Thank you very much. Thank you.
Thank you so much. Thank you to all the participants for actively participating. We will have a next session at 3:45. So if you have some work, you may leave for 20-30 minutes. Continue. We are not going to end this meeting, so it will be remain like this. In morning session, it happened because maybe the speaker has ended the program. We have given the authority as a co-host, so by mistake he has ended, I guess. So meeting will be remains on, and I advise you to join 5-10 minutes before. So next lecture will be given by Dr. Devapriya Das from IIT Kharagpur. That will start at 3:45, and his title is optimum sizing and placement of DGs, shunt capacitor, and EV charging stations. So kindly join that session. I hope it will be very informative. Thank you so much. It's now break for 20-30 minutes. We'll resume next session at 3:45. So please join on or before that. Who have already joined, you may remain connected, but kindly mute yourself. Thank you. Thank you so much.
Can you hear? Can you hear now? All of you can
Yes,
hear,
sir.
no?
Yes, sir. Yes, sir. Yes, sir. You are
Okay.
audible now.
Okay. Hold on. Let's be way
Okay.
back, no? Just let me share.
Okay.
Just,
Okay.
just
You just check, sir. Yes. Yes.
just hold on.
No, it's okay, sir.
Is it visible?
Should come, sir. We are waiting.
Can you see my screen?
Not yet, sir.
Can you see? No?
Not yet, sir.
Just hold on. What mistake I have?
Just you will find, sir, share button there. Are you able? Yes. Now it is coming, sir.
Now
Now
it
it is
is
coming.
coming,
Yes,
no?
sir.
Okay.
Yes, sir. Yes, sir. We can see your slides, sir.
Okay.
Sizing and placement of digits. Is it, sir?
Yes.
You can scroll one, sir. It is either changing or not. We can check that one also. Yes, sir. It is changing as well, sir.
Hold on. Is it the?
Is it changing,
Is
sir?
just.
Yes. You can cross check, sir.
Sorry, because we are accustomed with Google Meet or
Yes, sir.
Microsoft.
Yes, sir. I understand.
Acha, echo is coming. How to reduce this?
Some echo is coming, sir. We are listening very properly your voice, sir.
Echo is coming. Just hold on. I'll manage it.
Okay. Your screen is shared, sir. So we are.
I'm going on top.
Okay. Yes, yes.
This was shared. No.
Yes,
How
yes,
to?
sir. Now it is visible. Yes, sir.
Now it is okay.
Yes, sir.
But something has gone on top of. I am not expert. No.
Okay, nice, sir. Yes, I can
It's okay, no?
understand. Yes, sir. Yes, sir. You are on first slide, sir. First.
Okay. Just to give brief introduction,
Yes,
I
sir.
will
Yes, sir.
start.
Yes, sir.
Okay.
Okay, thank you so much, sir, for accepting my request to be a speaker for one of our sessions, sir. And it is sponsored. This FDP is sponsored by Atal Academy. This is thanks to them also. And dear participants, today with us we have Professor Dr. Devapriyo Das from IIT Kharagpur. He has received the B degree in electrical engineering from Calcutta University, Kolkata, India. The MTech degree from the Indian Institute of Technology, IIT Kharagpur, India, and the PhD degree from the IIT Delhi, New Delhi, India. He is currently a professor with the Department of Electrical Engineering, IIT Kharagpur. His research interests include autonomous power generation system, microgrid, electric power distribution systems, and EVs. He has guided more than 21 PhD scholars. He has published more than 180 research articles in various reputed journals and conferences. He has also written one textbook on power system and a few book chapters. The total number of citations for his published work is crossed the mark of 8,000. So thank you so much, sir, once again, and warm welcome to this FDP for your talk, sir. Thank you once again, sir.
Okay. Thank you very much.
Thank you, sir.
Let me tell you one thing.
Yes.
When I gave the timing, it was 2 hours, but
Okay,
we
sir.
have a meeting at 5 o'clock, right? So I can go up to 5 or 5:10. Huh?
Okay, sir. So in
So
10 minutes,
when
okay.
I gave the time, I was free.
Okay,
but
okay. No,
day
no,
before
sir, understand, sir,
this thing
understand,
has
sir.
come. Okay,
Your
okay.
busy schedule, we can understand, sir. So just
Uh,
5-10 minutes before 5-10 minutes before, you can leave the session.
I'll try to close at 5:55, right?
So 5-10 minutes, maybe participants may ask some question.
Whatever it is.
So I will try to remind you, sir, around 4:5
Ah.
or something like
The
that.
watch is there in front of me. I'll be
Okay,
knowing.
thank you so much, sir.
Okay.
Thank you so much, sir.
So, good afternoon to all of you. Right. And whatever I'll talk, I'll try to avoid mathematics for this. And I do not have any PowerPoint slides or anything. Whatever doc file I had, I have just converted to PDF. And wherever I used to give such kind of lecture, I always have given using chalk and duster. Right. So no PowerPoint. Wherever I have given anywhere in India, only chalk and duster. Right. So so here also I'll try to avoid mathematics and other thing, but I'll tell you something. Right. So that is sizing and placement of DCs and capacitors and other things at the EV charging station. Actually, if you look into the article of latest research, you will find that most of the electrical engineering is actually changing like anything. For example, nowadays hot topics of research are virtual power plant, right? Then your microgrid, then the electric vehicles, right? Demand response. So all sort of and of course that all renewable energy sources, right? Right. So and of course another thing is there, that is wireless power, right? So when not today, but it is coming up. But those who are young, when they will come to my age, at that time wireless power will develop like anything, right? So sometimes I imagine that the way today you are calling using mobile tower, maybe one day such kind of thing will come when wireless power one will get. For example, say electric vehicle, when it is running through highway, automatically its battery will be charged, right, through wireless power. So this kind of thing we can imagine, but it may happen. It may happen, right? So whatever little bit I will talk about that placement of DGs, sun capacitors, or little bit of EV charging station regarding electric vehicles. Something more we have done. I mean, my students are there, but those are unpublished yet. Only little bit I'll talk to you. So whenever talking about DGs, particularly we have renewable DGs like solar and wind. Biomass is also renewable but dispatchable, while as solar and wind, it is non-dispatchable. That means power generation is intermittent in nature because it depends on the nature. Solar depends on the sunshine, and wind of course depends on the wind speed, right? So whenever we are trying to optimize, DGs, although in this what lecture I didn't mention that whether it is solar or wind or anything, we didn't mention anything. Just we have considered it as a DGs, right? So if we take solar or wind or biomass separately, then we need to do some cost benefit analysis and economic analysis, and everything we have to look into that. So in this case, how we thought that whenever we are trying to locate EV charging station and number of electric vehicles, of course in electric vehicle different type of batteries are used. Here we have used only lithium ion type batteries, right? And that characteristic of that battery was used. But initially, and whenever suppose you have a distribution system, and suppose many electric vehicles are running, but you have to locate the proper location of EV charging, right? So together, if you want to optimize disease, then sun capacitors, then location of EVs, then how many number of EVs will be coming, then the problem will be very complicated. So what we have done, that problem actually broken into two parts. First, you consider DGs and shunt capacitors, optimize those things, and placed on the distribution network. Once it is done, based on certain criteria, you have to minimize certain objective function, right? After that, when you are connecting EVs, right, and you are trying to find a location, and when EV is getting charged, at that time, your load will increase. Load will increase, right? So naturally, voltage will fall, loss also will increase, but we have to go some compromise. So in this case, some fuzzy formulation we considered. So this fuzzy multi-objective thing, fuzzy things came long time back, but many years back when I was young, at that time, I formulated this fuzzy multi-object thing for network reconfiguration of distribution system, right? So your what you call, there are different objectives, different techniques are there for optimization. So optimization means either you can follow depending on your problem formulation, that whenever you are using fuzzy multi-objective, one better way of optimization is that fuzzy max min principle or fuzzy min max principle, right? Max min or min max, it is it is identical, but representation will be different, right? Another way is you formulate the fuzzy objective function, right? And then you try to optimize it using some optimization technique. For example, some soft computing technique. So whatever we have tried, in the article it is written, but I'll not show that. One is genetic algorithm, another is your grasshopper optimization algorithm, another is, of course, pioneer thing is, that is your particle swarm optimization technique, right? So genetic algorithm, actually when I was young, maybe in the year 1996 or so, that means 25 years back, at that time I wrote the code of my own, right? Actually, I used to write code of my own till my age of 48 or 49, right? Nowadays not doing it. So based on that, I have some experience about the coding, that how things are, right? But today I am not doing it. Maybe I have forgotten also most of the things, but I think I used to write all code of my own, right? So question is that this kind of thought first we made. Then generally what happened, that whenever you are connecting DGs, if we assume, say for example, lagging power factor DG, so it will inject both real and reactive power, right? And when you consider shunt capacitor, so it injects basically reactive power, right? So whenever another case is, if you do not consider lagging power factor DG, rather than you consider unit power factor DG and combine shunt capacitor, right? Then also it will serve your purpose. So real power injection means it will draw less power from the grid will be relieved, right? And naturally your power distribution power loss will reduce. Of course, you are not going for more DG power injection, that thing may happen reverse. So you have to consider certain criteria, right? And shunt capacitor, so it basically injects reactive power, right? Therefore, your basic purpose of shunt capacitor is to reduce the power loss of the network, and though not much, it improves the voltage magnitude, right? If you think about series capacitor, although not in use in distribution system generally, right? So series capacitor purpose is to main primary objective is to improve the voltage magnitude, but and though not much, it reduces the power loss, right? But anyway, primary objective is shunt capacitor is to reduce the power loss. That is the primary objective, and because of and your what you call that your and also it improves the voltage magnitude, right? Not like series capacitor, but it improves the voltage magnitude, right? So chalk duster is not there, but I cannot do also here. But if you are all of you in front of me, then on the blackboard and chalk, I should have explained everything, right? So now question is that how to formulate first DGs and shunt capacitor, how to formulate this one. So shunt capacitors, if you go to the market, you will not get in continuous rating. If you ask somebody that give me a size shunt capacitor of 21.23 kilovar, it is not possible. It may be available in a capacitor bank like 25 kilowatt, 50 kilowatt, 100 kilowatt, and you have to take 200 kilowatt, or you have to take a combination of those. Suppose 150 kilowatt. If it is not available, you have to connect 150 kilowatt and 100 kilowatt like this. You have to think about the cost benefit analysis. If it is a fixed shunt capacitor, then cost is less. If it is a switch shunt capacitor, then price will be high. Although we will not discuss here fixed or switch, because we have considered only the peak load condition, right? So all these things, whatever I said, all these things are written here. So basically, only example, any example you can take, these 51 bars or 69 bars, it doesn't matter, right? So ultimately, our objective is to see that how things are gone, and then EV load growth and other thing, and uncertainties. Although here, whatever I will show you uncertainties, that is using some, my student has done it, MATLAB thing, and some random thing generated in between some range. But anyway, that whenever you are thinking about uncertainties, if the disease is renewable or load uncertainties, right? So we are wind power generation. We have here we are not going to discuss it. We only go for probabilistic thing. Another is Hong's point estimate method, right? Anyway, those things, nothing is here, right? So, but anyway, to give a flavor, some kind of uncertainties we have generated, but not those techniques, not using those techniques, right? So whatever is what we made. So these introductions are very common. That why you are going for your what you call your solar or wind, right? Because day by day the conventional fuel will be or what you call increase decrease. So the resource will decrease, right? Therefore, our main objective should be that you follow that you just slowly and slowly you bring those alternative power sources like solar, wind, biomass, fuel cells. Of course, battery is also getting very your importance nowadays, right? So, the placement of DGs at inappropriate location result in greater power losses and cause magnitude reduction of in voltage profile, right? Therefore, there are several techniques available in the literature to find out suitable locations, right? So whenever if you try to find out locations, you have to, location means it's a number, you have to go for integer variable, right? Even for capacitor also, it is because of, it is available in the discrete form, like 25, 50, 100, I told you. So there also it is in discrete in nature. If you go for location, of course, you have to go for a integer variable. But if you go for a discrete one, that is better. If you go for capacitor one, for capacitor case, if you go for continuous optimization, you can do that. But for example, if you get something is 107.4 kilowatt, you have to choose the nearest size, either 100. 100 is the nearest one. If you get 118 point something, better you choose 125, because in the market you cannot get that 118.7 or something, right? So that, and another thing is many researchers, they have you studied the impacts of EV charging station on distribution system, right? And propose different charging rates and EV load scheduling methods for avoiding the overloading of the network components. Right here, we'll only hours and other things we have not considered that way for this lecture, but we are trying to do it something. All over the world, if you find a lot of research is going on this field, right? So if you just optimum DGs and shunt capacitors, we have used, of course, GOA means grasshopper, your grasshopper optimization algorithm, but we will not discuss anything on grasshopper, not discuss PSO, or not discuss of genetic algorithm. All these things are compared, but question is how to formulate that, your what we call that fuzzy multi-objective thing, right? That is the main thing. Now, whenever whatever is written, whenever you are trying to find out, that we have to look into this, how to formulate. For example, DGs, like your substation power, just hold on, substation power factor, right? DGs and sun cap, all these things. What you can do is that membership function, it is actually a degree of satisfaction. Meaning is degree of satisfaction, right? Suppose when you condition or constants are satisfied, then you maybe give unity membership function. That is your degree of satisfaction, right? So actually this concept of fuzzy, when I reading the little bit of history, I think one day Professor Jade, right, and he actually proposed the fuzzy concept in 1966 or 67, right, or 65 exactly. I forgotten. And along with his a friend. So if I'm not telling the name of his friend. He is also master of fuzzy thing, right? You can right. So when he found his friend was eating boiled egg, he found first one he is taking very easily. Second one also, this way when number of boiled eggs are increasing, then the degree of satisfaction is decreasing. Right. This is very simple. Anything you start eating, initially you will eat it comfortable. When your stomach will be filled, at that time your comfortness will go down. Right. From that thing, it came to his mind, I think, such kind of concept. Right. So whenever we are talking about your power factor of the substation, generally without DGs or shunt capacitor, distribution networks is drawing power from the grid, right? But what we want after the placement of DGs whatsoever, we want that power factor should at the substation should be 0.85. If it is below 0.85, its membership function will be 0, right? Then in between 0.85 to 1, right? That is, sorry, 0.85 to 0.95, we'll use, that is your membership function. 0.95 it is 1, that is desirable, right? And again it may decrease also, right, this way. So when power factor is increasing, when it is going above 1, not possible, of course, above 1, it is 0, right? So whenever you see this triangular membership function is considered for you power factor. You can consider other type of power factor membership function also. But in this case, we have taken the triangular one. If it is, for example, suppose your membership function is 0.5, right? So you may get two power factor. One is here, one is here, right? So you cannot you have to, that your what you have to do, that whenever you are putting something, you can, for a particular membership function you get two power factor, but whenever you are optimizing such things, you will get only one value. So accordingly you have to choose the power. If it is about 0.975, at that time it may become 0.5, or when it is 0.8 or 9 or so, right? So although this graph looks like your what you call symmetrical, this triangular thing, although it is not, because 0.85 to 0.95, so it is 0.1 difference, and 0.95 to 1, 0.0 difference. So slope will be different, but although in the drawing problem, it looks like this, right? But this way you have to represent, I mean, but other way also you can. Only thing is that our objective is that if it is below 0.85, we will take 0 membership. That is not desirable, and above 1, not possible. So, but anyway, it will be 0, right? This way we are representing this membership function for power factor, right? Similarly, the DG power penetration. Here also some minimum limit should be there, some maximum limit should be there, and this is also membership function mu PDGI, right? And this you have to specify what will be your minimum, what will be your maximum, and what will be your desirable, right? So this way you can, but other way also, other type of other membership function you can form, right? Different type of, but this is the simple way to represent, right? So this minimum, maximum, you have to define. You have to define, right? That is your, that it depends on you. That depends. Here also 0.851. It depends the way you want. Accordingly, you will get the result, right? Similarly, active power loss reduction. Suppose when it is minimum, when maximum, and beyond that it is zero. Suppose your, for a system, your power loss is 100 kilowatt, right? Suppose if you want, minimum should be, I want 50 kilowatt, minimum 50 or below that, then you define it is membership grade is 1, right? If it is minimum to maximum, this straight line thing is taken. If it exceeds that, then it will be, membership value will be 0, right? So that's why this kind of your membership function is taken. Anyway, you can take other type also, but this is another one, right? Similarly, voltage, minimum voltage, maximum. Suppose this is minimum voltage limit, this is maximum voltage limit, right? This is the, suppose it is, for example, this is 0.95 and this is say 1.05 or 1, right? So, but some VL1 and VL2 is taken. If voltage is below that, voltage magnitude at a particular, actually what happens in a system, you have so many nodes. Among that, you try to find out what is the min-max voltage, right? And accordingly, that's why it is given I V mu VI, right? If it is below that, then membership is 0. That is not desirable. If it is above that, above VL2, it is 0. So that is also not desirable. If the voltage is lying between Vmin and Vmax, then membership grade is 1. For example, suppose Vmin is 0.95 and Vmax is 1. So if all the voltages, I mean, all the node voltages are lying in between 0.95 and 1, then your membership grade is 1, right? So this is the concept, right? This way, 4 membership functions we have considered, right? After this, another thing is, I told you several years back when I formulated this for network reconfiguration of distribution system. At that time, although these are the not they are not the membership function taken, their things are different. Of course, voltage was there, then power loss reduction was there, then feeder unbalancing was there, overloading was there. There I use max min principle, right? And that results were highly satisfactory. There was no soft computing, and all these things, code, other things, all are it. Actually, many of you are students. Now today you are maybe doing research, maybe some of them doing PhDs. After that, you may become faculty also. After becoming faculty, if you are really writing code rather than using any packages, don't give up that habit. Right? Nowadays, many packages are available. Students using those packages, nothing wrong in it, but try to understand what exactly happens. You are giving input, getting output, but in between, everything is black box to you, right? Uh, what you need to know, what is there in the black box. Suppose you are solving some numerical methods, you are getting result like MATLAB Simulink, but how those things are solved, how state variables are given, if somebody asks you, you have to give the answer. That's why whenever you are writing code of your own, better don't give it up, right? Because nowadays we found that getting input and we giving input and getting output, that is okay, but at the same time one has to your ask the your understand the thing. Happens, some delays happen in waves, it happens, right? So now whenever, actually when I'm speaking, after that again I am hearing, right? So some delay is there. So whenever you read you are what you call, see the power factor thing. See, this is a equation of straight line, this is also equation of straight line, right? So whenever you represent this, when power factor is less than power factor mean, that is, this is power factor mean, this is power factor, then membership value is 0. So this is membership value is 0. When power factor is lying between this and that is your PF mean, and this is your mu f. This side, this side is PF. You find out the equation of the straight line, right? So if it is, and this straight line is true for PF between PF mean and PFD. This is your desired value. This PFD is the desired value. Here it is 0.95, but you can change it. This is PFD and this is PF max. And for this straight line, PFD to PF max, right? So that's why, so this is the equation of the second straight line. PF lying between PFD and less than PF max. But anyway, under any circumstances, this will never be go beyond 1, right? So if it is PF greater than 1, you can write mu is equal to 0, but you need not, better not to write, understandable, right? So this is for mu PF. Now DG power penetration. Now in this case, DG penetration PD is expressed into, that is your sigma, your I is equal to 1 to number of DG PDGI divided by sigma J is equal to 1 to BN PLI. This is total load, and this is wherever DG you have connected, so that is your PDGI. So this is a ratio, dimensionless quantity, right? So here, let me see, this is figure 1B, right? If you see figure 1C is the active loss and figure 1D is the node voltage. So here, if you, from figure B, if you write, similarly you can write when PGDI less than PGDI mean, it is 0. Then when it is PGDI mean and PGDI specified, so that is your this straight line equation. I mean this is, if it is less than PGDI mean, mu is 0. If from here to here, PGDI mean to PGDI specified, equation of one straight line. Then another one is PGDI SP and PGDI max, we find out another equation straight line. And it's greater than PGDI max, then PGDI is 0. Mu is equal to 0, right? So that's why this objective function is defined like this. It is, if it is less than this, it is 0. If it is greater than this, it is 0. If it is lying in between mean and specified, this is the equation of the straight line, left hand side. If it is between specified and max, then right hand side equation. So this straight line equation, easily you can find out y is equal to mx plus c. I mean anything anyone you pick up, you can take y is equal to mx plus c. That is mu is equal to your m, and it is PDGI plus c. So 2 points you need. This point is PDGI mean comma 0, and this point means PDGI SP comma 1. You substitute, solve two equation, you will get m and c, right? So accordingly, you will similarly here also, here also, here also. So you will automatically you will get this equation, right? So this is for your power PDG power injection. Similarly, active power loss. So when you are active power loss determine loss with DG and shunt capacitor. So before that, base case, without DG and shunt capacitor, whatever was the loss, and after placing DG and this is the loss. So this value will be always less than 1, right? Desirable. So if it is given, if you look into this fuzzy objective function, right, this one, if it is less than this, then it is 1. If it is lying in between this and mean and max, then this equation of the straight line. If it is greater than that, then the mu is 0, right? So this is the equation. If it is less than this, it is 1. If it is lying in between mean and max, then it is this one. If it is greater than this, then it will be 0, right? Mu is 0. So this is third objective. Now fourth objective, voltage deviation. So here also, voltage also, it is something like this. Here, if it is less than 1, mu is 0. If it is lying VL1 to then V mean, you will get an equation of straight line. If it is between V mean and V max, it is 1. If it is between V max and VL2, equation of the straight line. If it is greater than VL2, then mu is 0, right? So 1, 2, 3, 4, 5. 5 segment, right? So in this case, if you see it is less than this one, it is 0. If it is lying between this and that, this equation. If it is lying in between this and that, totally satisfied, it is 1. If it is lying between this one, yeah, and if it is greater than that, it is 0. So something, this is actually user specified, right? It is you have to specify, right? We have specified something that this is 0.94, V1 0.95, max is 1.05, and VL2 1.06 are considered, right? If you change this value, result will be different. But we have to choose that you are right. I mean from your intuition or experience, you have to take the better value, right? Generally, we want voltage should lie in between 0.95 and 1.05. That is desirable, but 1 is desirable because whenever at substation, if we assume the voltage is 1 per unit, in reality it is not. Generally, it is little less, but if we assume 1, right? So we want that all the node voltages of the distribution should be around 1. That is desirable, right? Different objective functions are there. You can try to bring it, right? So now we define the fuzzy voltage limit of this. Mu v will be minimum of that, because you have so many nodes. So every node has voltage magnitude. You have to take the minimum of all. That's why it is minimum mu vi. I is equal to 1, 2, 3, 4 up to number of NB. It is not mentioned here, but this is the thing, right? So now what you do, that there are four objectives. So each objective is multiplied with weighting factor W1, W2, W3 and W4. In general, all mu's are lying in between 0 and 1. Therefore, you can make it like this: W1 plus W2 plus W3 plus W4 is equal to 1, right? But in this case, when you are making, the already 4 objectives are there. Apart from that, you are trying to find out DG location, DG power injection, shunt capacitor location, shunt capacitor reactive power injection, right? These 4 unknown. Along with that, W1, W2, W3, W4 can also be optimized using any soft computing technique. In that case, total number of variables will be 8, and it will be very complicated one. But for each W1, W2, you have to set the limit. At least 3 of them you have to set the limit, right? Because that condition, a constant has to be satisfied. W1 plus W2 plus W3 plus W4 is equal to 1. But in this case, all W1, W2, W3, W4 all are given equal weightage. That is 1/4. That is 25%, right? But for 2-3 variables, for some other problem, we have tried to optimize weighting factors also, and you will get more or less desired result. And as all the mu values here are lying 0 to 1, then in this case, optimization of W1, W2, W4 will be easier. But if you put suppose voltage in kilovolt and loss in kilowatt, suppose 2 objectives are combined, right? You do not know when you formulate quadratic function that which one will be much higher than that. At that time, very difficult to select your the weighting factor, right? So better is you try to normalize in such a fashion such that each objective value lies in between 0 and 1, right? So in this case, this one was your W1, W2, W3, W all are taken is equal to 0.25. So the if you add all 4, it is 1, right? That means equal weightage. That means equal importance is given to each objective, right? So this way, similarly, PDG, IDG, minimum is 0. You have to set some maximum limit. Similarly, capacitor also, minimum is 0. You have to set some your what you call that maximum limit of the capacitor, right? Now, modeling of electric vehicle battery. So this is one way. Result we'll see later. So this objective was optimized first, right? And your results are given. Later I'll show you the result. So optimization thing using PSO or using genetic algorithm or using your grasshopper optimization, those I will not discuss. I have totally deleted from that, right? And nowadays, though, many packages are available. People are giving this objective function, load flow program, everything, and automatically things are calculated, right? But some cases you have to, so when things are not available in anywhere, there you at that time you have to write the code, right? So next one is that modeling of electrical battery charging load. So actually what happened for charging the impact of EV charging load on distribution system and analyzing the transient, we are not considering a transient, right? And steady state changes, it is necessary to develop EV battery charging load models for the load flow studies, right? So load of EV charging depends on the number of vehicles and the initial state of charge of EV batteries, right? Anyway, suppose you have a EV charging stations, many vehicles are coming, suppose if electric vehicles, different vehicles will have different SOC, state of charge. So what kind of, who will get the priority, right? Right. And second thing is, when they are going to charging station, it is also not a fixed number, it is a random, so uncertain quantity, what is right. So many issues are there. Anyway, those things will not be discussed because many things little bit we are doing with my student, and so it is unpublished, right? So in the present case, it is assumed that all the vehicles will recharge from fully discharged state. This is one assumption has been made, but note that this assumption is not true. Suppose one vehicle is coming with SOC of 30%, another vehicle is coming with SOC of 20%, right? So different vehicle have different SOC, so that will that you have to your what to call consider those effects, right, beyond the scope. But one or two of my students are doing those things, right, but beyond the scope of this. The characteristic of EV power charging demand and related state of charge for different types of batteries are shown, right? For example, lead acid battery we have taken from different references. Battery has 27.19 kilowatt hour. Lithium ion, that is Nissan Ultra, 29.07 kilowatt hour. And NIMH Toyota, 32 kilowatt hour, right? Charging capacities when they are finally charged from a fully discharged state. In this work, PQ model for battery charging load is developed by the characteristic of lithium ion batteries, right? These characteristic we have taken from one article, right? So if you look into this article, this chart, this is we have taken from a reference. It is not our thing. Later at the end or somewhere reference is there, right? So this side is battery charging kilowatt, right? This point is 6.5 kilowatt exponentially say, and after that totally flat, right? So this is time of charges 4.5 hours, and this is percentage of battery SOC. This is your this dot dash line, right? So and this is your 4.5 hours, and after that it is 5 hours, right? Time of charging hours, right? So anyway, so this is a state of charge, and this is battery power, and this is time of charging, and this part is exponential, say. So thick line is power charging, and dotted line is state of charge, right? This we have taken from one article that is from lithium, and based on that we have tried to do something, right? So charging characteristic of lithium ion batteries, that from actually one typographical error is there, right? So which one should be, this is actually should be TM1, this should be TM2, right? But here in equation some typographical error is there. Anyway, so PV max is equal to 1 minus e to the power minus alpha t your what to into divided by TM2. That is, this is exponential we have taken, so 0 to TM2, and then this portion is a straight line. So it is TM2, TMT to TM max, that is 5 hours in this case. It is equation of a straight line. It is for between TM2 and T max, right? And it is 0 for T greater than T max. So this thing we have taken from a reference article, right? It's from lithium ion batteries. While PEV is the instantaneous EV battery charging load, and PV max is the maximum battery charging load on the substation, right? Therefore, that beta I will define later. into PV max is equal to PV max, and this 1 minus e to the power minus alpha Tm1 by Tm2. This is actually Tm1, this is Tm1, right? And this is actually Tm2, right? So if you look from Tm1 to Tm2, this is actually flat, right? So now in this equation, Tm1, Tm2, Tmax, Tm1 is 0.25 hour, it is marked. Tm2 is 4.5 hour, and Tmax is 5 hour, taken from that article, right? So in this case, where alpha and beta are the EV battery characteristic constant. So beta is the fraction of maximum charging load, and the value taken as 0.95, which accounts 95% of PEV max at time T1. This we have assumed. So that's why beta into PV max is equal to PV max 1 minus e to the power minus alpha Tm1 Tm2, taken from that article, right? Now if you take your what you call beta is equal to this, or 1 minus e to the power minus Tm2, then you take natural log, then alpha can be computed from this minus Tm2 upon Tm1. You take PV max, we cancel, take natural log, then alpha will be minus Tm2 upon Tm1, then ln 1 minus beta, right? So this way, and this way we have tried to make it. But let me tell you, we have assumed that all the EVs which are coming, their initial state of charge was 0, which is reality, it is not. That's why we are trying to formulate considering uncertainties, but that is beyond the scope at present, right? So value of alpha, I told you how to calculate. Therefore, when the batteries are charging from an initial state of charge, suppose earlier this was initial charge was 0, but if you have that some initial charge PEB 0, then what will happen? That TFC, like alpha T now TFC minus alpha T upon TFC. TFC is the time taken for fully charging the battery from initial charging position. The state of the power charging battery can be expressed by the following equation. The SOC T plus state of charge at time T plus 1 is equal to SOC at T plus T plus PV, the electrical power T, into delta T, right? This is the state of charge. So this way, these equations are taken. So the SOC equations is straight line shown here, right? So in the now question is that conventional battery chargers will operate at lower power factor, and hence they require more time for reaching 100% charging state of the batteries, right? Hence modern battery chargers are use power factor correction techniques for improving the battery charging speed. So in this work, actually it is considered that battery chargers operate at 0.95 power factor lagging. So battery charging load at the identified optimum locations can be expressed using this during peak charging condition. That is PLEV NI, it is equal to NVI into PEV max. NVI is the number of vehicles and NI is the number of nodes, right? Similarly, QLI, Q is equal to, Q is equal to P tan phi. Therefore, QLEV NI is equal to NVI into P max into tan phi, right? So where NVI is the number of vehicles at the ith optimum node, Ni, PV max and phi are maximum EV charging load and power factor angle, right? We have considered 0.95, right? So PLV Ni and QLV Ni are the real and reactive power loads of EV batteries at the ith optimal node. So peak charging load is considered because we have considered peak charging load to determine the impact on distribution system performance during peak hours. So of course we have not used any transient thing, right? But actually when electric vehicles are coming, it is not all the time peak hours. So this is another assumption. That's why when you do such kind of analysis, one should consider annual load profile of the distribution network, and it is very kind of computationally it will take more time, right? It will take more time. So you have to, in your laptop or desktop, if you want to run code, then it will take more time, right? So anyway, so in the second stage, whatever it is, that first stage optimization is done, result we'll see later. The when optimum placement of EVs is right and number of locations. So whatever first what you do, this is LEPV, that is real power loss when DG, SC and electric vehicles all are there. DG, SC are already optimization done. Now EV is kept. So loss will increase. Loss will increase divided by loss when DG and SC both are there. Right. That means this one will increase. That is greater than 1. This one, because EV is load, suppose it is 100 kilowatt, you have connected some load, so loss will increase. So this value will be greater than 1. But you cannot allow it to go as far, you have to restrict it. This way we thought, because we thought otherwise we cannot formulate the problem, right? Therefore, your LEPVI, EPD is the real power loss when EVs, DGs and shunt capacitors all are there, and this one when the real power loss with DGs, right? So now you define the membership function for real power loss with electric vehicles. If it is loss is minimum that, then mu is 0. If it is minimum loss lying in between the minimum and specified, then this state line. And if it is in between specified and this one, your loss PVI max, then this state line. If it is greater than that, it will be 0. That means when DG and shunt capacitor you connected, our objective was to reduce the loss. But when you are connecting EV, loss will automatically increase. But we have to restrict it to get the desired result, right? So this is the equation. If it is less than that, it is 0. If it is lying in between mean and max, this is the equation of the state line, membership function. And if it is lying between this is the right hand side state line equation. This mu will be this one. And if it is greater than that, this is 0, right? So power loss will increase with EV load. Therefore, LPEV, I told you, will always be greater than. So in this case, 50% increase in power loss during peak hours is allowed. That means if it is go beyond 50%, that is not desirable. We do not. Then if you connect more EVs, and then what will happen? Voltage also will decrease, right? So this way, and another thing is that where it has gone high in power during peak hours is allowed compared to the case with DGs and shunt capacitor, and the values this LPI mean specified are taken as 1, 1.5 or 2. That means if it is this is 1, then whatever it was there with DG and shunt capacitor, if it is going up to this, it is 1.5. But if it is below this, it is 2. It is below above this thing, it is 0. So that is our objective is to try to restrict within 50% of that, right? If it is 1, it should be 1.5. If it is 100, it should restrict to 150, right? All below that. That is that you want, right? And similarly for voltage, same voltage, whatever was given there earlier, same voltage you can put, but at that time minimum, I mean your whatever is there, that minimum, maximum, you can try to put in that range, no problem. And WL, the weighting factor, and WB, the WL plus WB is equal to 1, right? So you can put 0.5, 0.5 both, such that equal weightage. Here no question of optimization. So no algorithm is given, it is simply written, no algorithm is given. I didn't put anything here, right? Now the algorithm, actually this algorithm actually, the number of charging locations, number of vehicles, right? All these things, and charging station integer variables, right? Location also it's a node number, and number of vehicles also integer variables, right? Therefore, later if you want, I can send you that your this algorithm or your flowchart, everything, but nothing I have kept it here, right? So maximizing this objective function, first shunt capacitor and DGs, and second your electric vehicle. So two examples are considered, and the first is, look, we have considered the fuzzy your grasshopper optimization, fuzzy PSO, fuzzy GA, and two examples are taken, right? So 51 bus system and 69 bus. So these are the node number identified, and this is the DG sizing in kilowatt, and this is for shunt capacitor. These are the node number for 51 node, and this is the size. Look one thing, whatever 300, 240, 230, that means these shunt capacitors we have treated as a continuous variable. We didn't treat it as a discrete variable. That's why, and 240, 230 means we might have got 242.4, we have written to 240, right? That is the thing. Similarly, if you look into, and DG anyway, whatever power it will inject, let it inject. But what type of DGs, nothing is mentioned, right? Similarly, if you mention what type of DG, solar and wind, then in that case, whenever we are talking about DG sizing, something more I should like to tell, that if you go for a DG sizing, that suppose you are considering peak load, suppose you want to optimize solar your PV sizing, then whatever power injection you get at peak hours, that is not the size of the DG, right? Solar DG, because you have to consider one term called panel generation factor. Suppose you have bought 100 kilowatt peak solar PV plant. Do you think that solar PV plant will give you 100 kilowatt peak? Never. Maybe you may find most of the time in a year it will give 50 to 53 kilowatt, right? And generally you will find occasionally it may cross 70, maybe very rare, right? And if you take the average one for a solar, consider only daytime power generation, it may be 20 to 23. So if you get on 100 kilowatt peak, your peak power generation will be 52, 53, 54 kilowatt. Suppose if it is 423 kilowatt, suppose if it is solar PV, if you say size, then it is not correct. It's a size may be 750 or 800 kilowatt peak. Right. If you think about wind you have to consider the efficiency. A very rough idea I am giving. Then you have to divide it by efficiency. If it is 90% by 0.9. If it is a biomass DG, right, then it is okay, right? So, but here no DG size is mentioned. No DG size is mentioned. Similarly, for 69 bus, I do not have the diagram here, but in another slide, I think this 69 node bus diagram is there. 51 in our article, it is there, right? And for shunt capacitor, that is an integer variable, it is 69, 2 and 59, right? So these are the sizes. And if you see the other table for your different loss, your Phaji GA, Phaji PSO, Phaji G, all these things, if you will see, only thing is that if you try to see the result using different soft computing technique, you will find results are matching very close to each other, right? But it is not only one run, you have to make many runs. Out of this, at least 20-25 runs. Out of this, you have to pick up the best one, right? So all this result, if you look into that, it's like base case, it is base case. Now substation reactive power, substation power factor, total DG penetration, real power loss, voltage minimum magnitude, right? These are base case. But if you look other optimization case like volume voltage, 0.973, 0.9726, 0.9743, 0.97, up to 2 decimal place, you will find more, it is same, right? The only thing is that, and if you see the total DG power, it is 1147, this case conventional, then 12 or 31 point, then 12, 32, 12. So all are very close. All are very close. Here also, if you look 419, 415, 460, all only thing is that you have to see which one is the computationally efficient, right? So this is the your 51 node system, right? These are the result. Now, if you see 69 node system, you will get similar thing, right? All are very close, but later one or two graphs shown that which is better, which method is better, right? And actually coding, rather than using any packages, this PSO or GA or this one, it is very easy. You can write, if you know little bit of coding, easily you can write the code, right? Only few equations and no your like classical optimization technique, No need to find out gradient or anything. Simply you can write the code and get the result, right? So if you look into this is the voltage, this is your what you call voltage magnitude profile, right? It is actually, it cannot be a continuous graph. Like from here, it suddenly jumped here. That means it is the end of a lateral branch. Maybe it is going to another node. That's why it is this jump. So it cannot be a continuous plot. We always prefer that give us a bar graph, right? But anyway, just to, otherwise if we put bar graph, everything will become clumsy. That's why it is given like this, right? But bar graph is always better, right? Otherwise, from here suddenly voltage is jump here, say node 16, and maybe it is the end node of that 51 bus. Maybe another node is starting maybe 17, maybe somewhere else. That's why this kind of thing, right? Basically, you should give a bar graph for node voltage. Similarly here also. So all these things, if fuzzy grasshopper, all because how we wanted to highlight that. So that is the voltage. So basically you want voltage should be around 1 per unit, right? But nowhere voltage has crossed 1 above 1. If it goes 1.05, here also it has crossed some node, it has crossed a little bit above 1, right? Here for 51 it didn't, but for 69 some places it has crossed over, maximum is 1.05, right? Actually, uh, in many cases, in the light load condition, right, distribution system that they offer, that at the particular light load condition, that actually what happens, that voltage rise is very high, right? If suppose your limit is 1.05, it may go beyond that, right? To mitigate the voltage rise, if we suppose wind turbine generator system is there, wind power generation system, that wind should operate at the time in the leading power factor mode, right? Because that is required, because if it draws reactive power from the grid, then in each branch that reactive component of the current will increase. In general, current will increase. Therefore, there will be voltage drop will increase. Therefore, receiving in voltage will go down. To mitigate the voltage rise, they operate such kind of thing, particularly light load conditions, right? Anyway, those are beyond the scope, but I am just telling you, right? And whenever we are considering that your fitness function, that is your objective function J, and something is given, so we found that your fuzzy grasshopper is your what you call giving better result, and moving to the your what you call maximum value is your what you call earlier. This side is number of iterations, and this is your. But one thing, let me tell you, we have to run just one run doesn't give all the time best result. You have to run many, and after that you have to pick up the best one. Similarly, for 69 bars, this is also given. It's convergence, right? The number of generation or general number of iterations, right? This is the thing. So this all write-up is there. I'm not this thing. Now optimum size of EV. Now when you come to EV, the 51 bus, these are the locations are found, right? Optimum number, sorry, optimum node for EV. These are these things, and these are the number. Total number was 137 for 51 bus, and for 69 bus, total number of users 190. These all are optimized using your integer, same optimization technique, but we treat that as integer variable, right? So after this result, that with EV load 25% increase, with 50% increase, all these things are tested, right? So real power load, reactive load, and real power load for this thing, right? And EV load effect on minimum voltage. So just see the load bus factor is every load is multiplied by 0.4, 0.5, like same thing come to 0.1. Base case was 0.9. With DG and shunt capacitor, it was 0.9752. With initial EV load, it was decreased 0.9608. Now with 25% increase, it is 0.9564. With 50% increase in EV load, it is 0.9519. So voltage is decreasing, right? Similarly, For 69 node, taking only one, that is the peak load, 0.9092. Right. Then with DG shunt capacitors, it improved 0.9761. But with initial EV load, it was 0.9659. After that 25% increase, it is this much. With 50% increase, it is this much. Right. So this way, we have tried to optimize that number of location numbers and number of electric vehicles. Right. So that EV load effect on real power loss. Right. So base case it was 19. And with DG shunt capacitor, come to one, only one amps peak load. Base case it was 129. With DG and shunt capacitor 32.8. With the initial EV load, it was 64.5. It is doubled, right? Right. With 20% further increase, 78.1. With 50%, it is 91. Because load is increasing, so naturally loss will increase and voltage will go down. Similarly, here also 69 node, you can notice that with the 225, this is base case, DG shunt capacitor 27.34, with initial EV load 41 in this case, 25% 46, with 50% 53.9. That means 51 node is lossy network, because look, increasing that loads are different, and here even we increase that, it is going to almost double, 27 to 53.99. Then here it is 32 to 91, nearly three times, right? So EV load effect on real power requirement from substation. Just consider one base case, it was this much. With DG shunt capacitor is this much. With initial EV load, it is this much. With 25% is this much. But with 50%, it is 2600. That means it is more than, slightly more than this one, right? And this is for 69 node. 69 node one base case, it was this one, but with 50% even it's 3813. So I mean it is less than that. Of course, it depends on the network and network's load, network's R value, X value, so many things, right? And power factor of the load, right? All these things, it varies. So this is actually EV load effect or reactive power requirement for this is actually a reactive power thing. That was real power is given. This is reactive power was given, right? So these are all. Actually, time is closing. These are all. So, some other bar graph is there, that your minimum node voltage, how it is not colored. It should have been colored, right? Actually, I think it was colored, but I have taken something, so it is color is not there, right? So in any way, this is bar graph was showing that that is base case is that blank one. DG and SCs is the your gray one, right? And EV's load is this thing is the black one, right? So generally with EV, loss will increase, right? Because it is a load. Similarly, but different percentage of loading, node voltage, everything is given, right? Similarly, some voltage magnitude, charging station 1, 2, 3, 4, 5, how things are happening, that is also given, right? So this is the number of hours, and this is voltage, right? So this is number of hours, and this is voltage. So this battery charging time hours, and how voltage per unit is giving that minimum voltage. This is actually this how time your voltage is changing, that certain things we did something. Suppose that every hour power suppose you are doing some iteration method. So like your transient stability, the way one can evaluate that power will be injected, right? Here it is giving hour 1, hour 2 like this. Suppose you are using some simulation study, suppose some power, suppose some state variation dynamics. So that also you need the load flow. So connect it to the network. After that, when you are solving it, every second you are getting output power, every iteration. That is your simulation integration time, maybe 0.01 second or 0.005 second. You inject that power, and every time you see the voltage. Accordingly, you can plot it. Here I cannot tell you how I need time, but we did it, right? So anyway. So these are given that your minimum voltage, and for 59 charging thing, that up to 4.5 this, then 4.25 hours this, right? So this is your voltage transient is shown using those equations, right? Anyway, and this is randomness. Something was generated, but let me tell you, for uncertainties, we have to learn certain mathematics. Either maybe probabilistic, either you have to create some scenarios and you have to select something, or you have to go for Hong's point estimate method. So many things are there, like load also uncertain. If it is renewable DG, then it is also uncertain, power generation uncertain. All these things, if you take, the things will become complicated, right? But anyway, by mathematically people will appreciate. Then your correlation, correlation between solar and wind, solar and load, wind and load, right? All sort of correlation. For that, if you are interested, you can see one article called Nathap transformation. It is highly mathematical, but we have done it and we have seen the correlation. That is called Nathap. It is a mathematics paper, but you can apply there. Nathap transformation. Right. So anyway, conclusion I am not telling. Some references are there. I should have put more references. Right? More references are there. Right. So with this, time is not there. Otherwise, I was thinking something about this virtual power plant and microgrid. Both these things I should tell you, right, regarding difference between virtual power plant and microgrid, because virtual power plant things are coming up and new research topic, and something on island microgrid. My students have done something on electric vehicle and island and microgrids, but unpublished. I cannot tell. So little bit I told you, right? And that's all. If I had to tell you all these optimus things, that it will kill more time. Thank you. I actually I am grateful to Kundan because he gave me 2 hours time and I had also time, but unfortunately another meeting has come just at 5 o'clock. Tell me if you have anything, you just tell me.
Okay. Thank you so much, sir. Let's see if few questions are there, or else we will share your email ID if they needs to ask some question.
And many participants, I will. Initially, I saw many participants.
Sir, no
Yes, sir,
question,
yes, sir.
but sir, no question, but it was a good question.
No, many participants are there. Last year, I gave one lecture, I think. Their participants were huge. I think that was the maximum. Nearly 200. Nearly 200.
Yes, yes, sir. Yes, and actually, sir, this time is running semester is going on everywhere.
Yes,
sir.
yes,
So
yes.
it's 50. This morning there were 100.
Yes,
So
yes.
like that, sir, faculty is having some classes and all. So
Yes.
sometime also it is very difficult to attend.
Yes,
So thank you so much, sir, for
thank you.
accepting my request. And
Manipur, I went once.
okay,
That
sir,
was
okay.
that was maybe 4 years or 3 years back.
Okay, I was not there
At that time,
earlier.
you are not there. Location was very good. Location is very
Yes,
good.
sir. Still weather is very good, sir. Here everything is
I
like.
went. I went.
Yes, sir, yes, sir. So once again, sir, thank you so much for your support, sir, and for your
Thank you.
nice lecture. Just I am sharing one. Uh, Still, you are busy, sir. You don't have that much. So thank you so much, sir. A token of appreciation.
Thank you.
Other things I will send you in your mail, sir. Okay, sir.
Okay. Thank you.
Thank you so much, sir. As you are busy, sir. Actually, I did my PhD under Professor Giuseppe Buja in Italy, sir, from Italy. And there I have worked something like a propulsion drive system as well as just charging system. So we are talking about that dynamic wireless charging system. So me and my scholar who is are working under me, now we are developing something on dynamic wireless charging side.
Yes.
So that is really very good thing to start something there. So anyway, sir, I will invite you in some other time, sir.
Let the things become normal. Right.
Yes, sir. Yes, sir. Yes, sir.
Let
the
things die down as early as possible. We pray that it should die down as early as possible.
Yes, sir. Yes, sir.
Okay.
So once again, thank you so much, sir.
Thank you.
Thank you so much.
Okay, sir. Okay. Thank you. Then leaving here.
Thank you. Yes, sir. Yes.
Thanks, sir.
Okay.
Sir.
So thank you so much, all the participants, for your tireless session from since morning to evening. We understand that you have many other responsibility with this, as many people are working either in industry side or in academy side. So thank you so much for your kind presence and enjoying the lectures from the eminent persons. So tomorrow we will start at morning 10, and that session will be handled by actually tomorrow Dr. Ravindra L. He's a scientist. Actually, he will be taking lecture, and that lecture is EV powertrain system and performance evaluation using drive cycle analysis. He has done his PhD from IIT Guwahati. So of course we will see, and I'm sure that his deliberation will be very interesting. So kindly join tomorrow at 10 a.m. And tomorrow we have another 3 sessions, one at 10 and again 1:30. Similar way we will go. So tomorrow evening we will have 3:45 to 5:45 a motivational and spiritual session. That is a title for that is Mind Secrets. So kindly join that one. That will be very interesting as well. So once again, thank you so much for your kind cooperation. When you are so busy, everyone is busy with their different work. So thank you so much once again. If you have any query, any question, you may put in a WhatsApp group or in my mail or anywhere you can put. So I'm trying best. I'm trying my level best to collect the PPTs from the presenters. If they will give me that, I will be shared for sure. Or else we will be uploading or sending the video lectures. Because in video lectures, you may see how they are explaining, like what are the explanations also you will find there. So I will try my best to support you, whatever possibilities is there. So once again, thank you so much for your kind cooperation. Thank you. Thank you so much. So today's session is we are closing now. Tomorrow we'll see 9:30 onwards. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you so much. So now we are closing the meeting. So the meeting will be ended. Okay. Thank you so much.